I got you. I got you.
You got me? All right, cool. Woo.
Yeah, you just yelled at me, so you're recording.
Would have been, all right, cool. Let me go ahead and pull this up just in case. Yeah, good save moment. All right. So binary trees is a data structure that's kind of similar to like a linked list, right? You have your root, you have your nodes left and right. Your left child and right child are going to be a part of the tree, correct? In a binary tree, each node has at most two children. You can't have a node that has three children, four children. You'll get to that when you get to CS2. But for now, just understand that a binary tree can only have at most two children, all right? There is no strict rule about how the elements are arranged within the tree. And then you have your operations searching, insertion, and deletion, all right? These operations may not be as efficient, especially if the tree is not balanced and you have a time complexity of O of n in the worst case scenario, where n is the number of nodes in the tree, all right? Now, the biggest difference between a binary tree and a binary search tree is binary trees, it doesn't really matter how you have them kind of like set up. So if I have let's say a root of 30, but my left child is like 65 and my right child is 6, that is still valid for a binary tree. However, in a binary search tree, that isn't allowed because a binary search tree needs to have a set structure. Now, your root is always going to be whatever number you set your root to be. However, the right side of that root is going to be larger than the parent node, if that makes sense. The left child is going to be less than that parent node as well, right? It's essentially what it is. As for binary search trees, they have a time complexity of O of n. Do your best to make sure that you guys really understand the run times of these operations, because more than likely they might actually add. Yep, there you go. Binary search tree average of and login and then O of n. Just make sure you guys understand that, okay? Let's go ahead and go through. All right, so I'll talk about the properties of a binary tree. The height of a binary tree is defined as the number of edges from the root node to the deepest leaf node. The height of the binary tree is the length, essentially like the length of the longest path from that root node to any of the leaf nodes. The height of the binary tree can also be known as depth. So if you see a question on the test that says, give us like the depth of a binary tree, yeah, meow. Just know that that can also mean height. In a full binary tree, every node except the leaves have exactly two children. So it could be two children or less. It could be one child on the left, one child on the right. In a full binary tree, all non-leaf nodes have exactly two children. This means that there are no unary nodes in a full binary tree. All right. So one other thing to mention is in a binary tree, all levels, for it to be a complete binary tree, all previous levels have to be filled. So if I have my root node, it's left and right child, and then that left child has two nodes, and that right child also has two nodes. But then that left child has like two more, the other left child. Wow, this is going to be easier if I just explain it with the whiteboard. But essentially, all levels have to be filled. I'll show a picture of it in a few, but
if you press Shift and L, it turns to draw mode during presentation. So Shift and L.
You said, oh, Slack.
Hold Shift and then press L, and then now your cursor is now a marker.
There we go.
What is that?
I have no idea. I'm on a MacBook.
Okay.
So
is that sidebar? Shift L. I guess that's a binding for. Oh, there you go. Now you can draw with your mouse.
Oh, okay, cool.
There you go.
All right, yep. So
fire.
You better pray I got these skills. Hold on. Y'all ready for this? Cool. All right, let's say we have a binary tree like this. I'm also doing this on a trackpad, so got my mouse at home. Say we got this, right? This is going to be considered a complete binary tree right here. This is complete. All levels are filled. Now, if I have, boom, and then this has a child right here, this isn't going to be considered a complete binary tree. It'll still be considered a binary tree, but not a complete one. A complete one would mean I'd have to have these nodes right here. Again, my explanation of this might be weird, and so is my drawings, but I'm on a trackpad. But does everybody understand what I mean about this? And then I think it's Shift L, you said. Let's see. I really got to get used to using Zoom. Once up, let's go back. All right, we'll go over to the next. But of the properties of a binary search tree, the left subtree of a node contains only nodes with keys lesser than the node's key, kind of similar to how I explained earlier. If you have a root that says 30 and you want to insert, let's say 29, 29 is going to be less than 30, you'll place it to its left node. Same with the right subtree, it's going to have keys greater than that current node's keys. If we have 30 and we want to insert 31, that'll go to the right side. This means everything in the left of the root is less than the value of that current node. So I guess for now, we'll just say the root, and everything to the right is going to be greater. The left and right subtree must also be a binary search tree. So this doesn't just apply just to the root. This will apply to its children as well, and its grandchildren and great-grandchildren and more children from there on, okay? There are also no duplicate nodes in a BST. BSTs may have duplicate values with different handling approaches, though. And this is a diagram that I have here of a valid and not valid BST. So this would be valid, this would be invalid because we sent 6 down this way, invalid because we sent it to the 3 to the left side. Let's see. 1 second. Okay. So we'll go ahead and start with traversing trees. This is a very important concept when it comes to the foundation exam and just using binary trees in general. How does everybody feel with the binary search or the traversals? I'm actually gonna pull up the chat for this. Easy, cool, good. All right, cake. All right. So I'll just go over them briefly since a lot of people seem to kind of know what the traversals are. But pre-order traversal, of course, current, left, right. So we'll print, we'll traverse left, and then traverse right, and then we'll get 1, 2, 4, 5, 3, 6 based off of this tree that we have right here. And then if we go with the in order, you'll start from the leftmost node, 4, and then you'll continue up, traverse, print, left, and then go right. And then post order, same thing, except you're going to start 4, 5, 2, 6, 3, 1. Again, this is, it seems like everybody knows this, so I'm just going to do that. All right, inserting into a binary tree, right? So we'll take the following example. Let's say we have 100, 20, 500, 10, and 30. This is going to be our current binary tree, and we want to insert 40. The first thing we're going to do is we're going to compare that with the root and see if that what we want to insert is either greater than or less than the current node. In this case, since we're inserting 40 and our root is 100, then we're going to traverse the tree left and compare it with the next node and so on. So in the step 2, we'll compare it with 20. It is going to be bigger than 20, so then we'll go to the right, and then we'll check 30. Now, because 40 is greater than 30, we'll go to the right side of 30 and insert that node. All right? So this is essentially how insertion works. It's kind of simple, and I'm pretty sure most of you guys know this, but yeah, we'll go from there. All right. As for the deletion, we have the case where there's I believe about 3 or 4 cases. So we'll see in the slides now. So let's say we want to go ahead and delete 20. In the first case, it is currently a leaf node, so you're just going to assign that leaf node to null. Now, if it gets a little bit more complex where we delete a node with a single child in the BST, we're going to move its child up, replace it with, in this case, we'll move up 80, replace it with 70, or replace 70 with 80, and then we'll set 70 to null. So 80 becomes the new child of 50. And then case 3, where we delete a node with both children in the BST. So in this case, if we want to delete 50, we'll replace it with its in order successor. In this case, it will be 60. and then we'll go ahead and move 50 down to where 60 was, delete 50 by setting it to null. So I'm kind of like, okay, cool. So I'll go ahead and solve these two problems with you guys for now. For pre-post. Well, I have this pulled up. Dash method works too. Goes upon. There's a ternary tree. Yeah, there has. Okay, let's go ahead and solve this real quick. One moment, because I gotta adjust my stuff here. Unfortunately, I couldn't find a decent spot until 2:30, so I'm gonna ask that you guys bear with me. So we're doing the assignment. All right, cool. So let's go ahead and start this problem. Consider using the following struct definition for a node of a binary search tree. So they give us the struct node and it takes in data, height, our left and right. Assume that a binary search tree has been built with the data values in each struct filled in, but the heights are uninitialized. Write a void recursive function, assign heights with no helper functions, which takes in a pointer root to the root of a binary search tree and assigns the height component of each node in the subtree pointed to by root to its correct height in the tree. Recall that the height of a leaf node is 0, and that more generally, the height of a node is the maximum number of links left or right to follow from that node to any leaf node in that subtree. And then if root is null, then no action should be taken. All right. This is also going to be one of the first times I use Caleb's site. So let's see. Hey, Dylan, you're there, right? How did you type on this yesterday?
Yeah, what's up? If you could do that, but also if you just double click, it'll automatically spawn a text field for you.
Okay, that works.
Yep.
So we'll go ahead and take void assign heights. I can't spell root. Okay, so essentially this problem right here is trying to get us to assign the heights, right? And we want to be able to do this recursively. What do you guys think we should start doing for this problem? How do you guys think we should do this? Base case? Okay, so base case, right? So we'll always start with the base case if it's recursive, as from the last time we did this. What do you guys think that base case is going to be? If root left and root right is null. Okay, so not necessarily if root is equal to null. Okay, so I'm getting if root is equal to null and if root is not equal to null. So in this problem, it's saying if root is null, then no action should be taken, right? Based off of that assumption, meaning that if it's not null, then you would take action. Now you can do this base case of if root is equal to null, return null. However, it's also you can't return null, it's a void. But for the most part, your base case should be this. If root wait, hold on, break for it. Oh, if root does not equal null, there we go. So this is what you're gonna want to start off with. Since you're going with the assumption that like if root is null, then no action is going to be taken, then you can honestly do a base case of this because at that point they're just going to assume that it is it's not null. However, if you are on the FE and you want to do if root is equal to null, if you get a problem like this, if root is equal to null, then return, and then you have this case underneath it, this will work as well. They're not going to throw you off for that, nothing like that. But this is something that you can do, right? So we'll start off with this base case of like if that root is equal to null or is not equal to null, then what do you guys think we got to do next? Okay. And how do you guys think we check for leaf nodes? Now, I like the track you guys are on, but before we do that, we have to do something. So, all right, Damon got it right. So we do have to go through the tree. All right. So we need to traverse the left and the right side. And how do you guys think we're going to do that? Version? Okay, cool. Let's go ahead and recurse. Sign heights. Yep. Sign. So we'll go ahead and do that. Now we have the left and we have the right, right? Now, one thing that we need to understand in a binary tree or a binary search tree is that the height of an empty tree is going to be -1. Until you add that first node, you're gonna have a -1 for the height. All right. And you guys, yeah, you guys did good with the recursion part. So we'll go ahead and remember anytime that it's asking you to start looking for a height. So we'll do int height is equal to -1. You're gonna want to initialize the height. And then we'll go ahead and start going from there. It says height is 0. Yep, height is 0 because there is a node. But always start with -1, and you'll see why when we complete the problem, okay? All right, what's next? What do you guys think we should do next? Just a heads up for these problems, I'm gonna be asking you guys like what's next, and then if I see anything wrong, I'm gonna steer you guys in the direction because I want you guys to actually try it. And then I'll explain from there. Yep. All right, perfect. So we could do this check right here. If root left does not equal null, we can assign the height to that. So we could assign the height for the left side of the tree, right? Do the same thing for the right. All right. Now, there's one more check that we need to do for the right side of the tree, because if you look here, we assigned the, oh, did I put left? Sorry, just be height. Okay, there's supposed to be one more check here with the right side. So because the height is currently assigned to the current left's height, what other check do you guys think we need to do? Remember, because we're finding the height of a node is the maximum number of links. Think about this a little bit. There's one more check. Assign left and right height separately. Close, yeah. We will be assigning the right height to the height eventually. But right now, height is the left subtree. Okay, yep. Ethan got it right. All right. So the next check you're going to want to do is to see if the current right height is greater than the current height which holds the left subtree. And if that's the case, you're going to replace height with root pointing to right, pointing to height. So we'll replace that, and height will now be equal to the right side. And that's only if the right side is greater than, sorry, one sec. I don't think you guys can see some of this. Might be easier for me to. If this starts to become a problem, I'll move it to like an IDE. But for now, we'll go with this. So we set the height equal to the right side. And that's if the right side is greater than the left. And that is because, in this sense, the right side has more links than the left side. All right. And then from here, what do we do? What do you guys think we do? I'll give you a hint. Yep. Cool. All right. Good job, guys. Let's go ahead and take a look at the solution real quick. If Zoom wants to, I'm just going to do that. Because remember, height starts at -1 in this scenario, and you're moving down. Remember, an empty tree has a height of -1. That's why I said, remember, you'll understand why I'm setting it to -1 early on, because here, this just takes care of it. Anytime that you deal with something with the height, just remember that the height will always be -1 on an empty tree. So then you'll set that, and then I'll show you guys the solution. Can you guys see it decent enough? Okay, cool. All right, does anybody have any questions about this question? I will answer them to the best of my ability, but it looks like you guys did really good in figuring this out. North? Okay, go ahead and move to the next question that I have prepped for you guys. Oh, wow. Go away. Sorry, guys, give me just one sec. Love it when you have technical difficulties. All right, and then we're gonna have legacy count. Definitely not. Also, yeah, I'm gonna give you guys a kind of like my predictions for certain questions at the very least. There was an AVL on the last exam. I honestly think they're gonna go with a try this time, just being real. Um, but just make sure that you can do both. Don't just hard focus what we think is gonna be on there. Just make sure that you're fluent with everything for the most part. And then as for the binary or the what is it, bitwise questions, they usually alternate. I don't think there's gonna be a bitwise question on this one. It's more than likely gonna be a base conversion. Just a heads up. Yeah, nah, I'm with you. You are allowed a scientific calculator. Now, hang on, let's not celebrate too early because we ain't seen this exam yet. Guha might do a 180, but just remember, just remember, you there's a scientific calculator that is allowed. Yeah. Now we love Guha. Do we get to use one? Like, it has to be the most. I was told that we were able to. I'll get back to y'all on that tomorrow's workshop. Well, yeah, I don't know where I got the info from. I forgot where I got the info from. I remember reading it in one of the documents, but it's all right. For now, assume no calculator. More than likely, you're not gonna need it. Just a heads up. Yeah, not straight up. 20 points on the FE for misinformation would be nice. Okay, let's go ahead and start this question. All right. The goal of a function named legacy count is to take the root of a binary tree root and return the number of nodes that contain a value greater than at least one of their ancestors. For example, this function would return 4 for the following tree since 60 is greater than both of its ancestors 3 and 4, or 3 and 14. 40 is greater than 2 of its ancestors 3 and 14, even though 40 isn't greater than its parent. 28 is greater than both of its ancestors, 9 and 14, and 2 is greater than only one of its ancestors. So it's going to return 4 because 4 of the values have ancestors that are greater. To make the code work, legacy count is a wrapper function for a recursive function called legacy helper. Included below is the code for legacy count, as well as the function signature for legacy helper. Write all of the code for the legacy helper function. Note if root is null, you should return 0, okay? So how do you guys think we're going to start this problem? Base case, yep, there we go. Perfect. If root is equal to null, we'll return 0. 3 points, yeah. Remember, your base case is more than likely going to be 2 points. Easy 2 points that you can get. Don't ever forget that you need a base case for something that's recursive, okay? All right, what do you guys think is next from here? Only 2 points I will get. It's crazy. Nah, hopefully you guys will be fine. Okay, that's how that works. All right. Okay, what do you guys think is next from here? After we check the base case, what do you guys think we need to do? Is bigger than, yep, perfect. So we'll go ahead and check that. If root, when in the data, is greater than min ancestor, what do you think we're going to be doing within this if statement? I'm letting you guys lead, and I'll tell you if it's wrong or not. I'm going to put our collective brains together for this one. Turn 1 plus calls again. Perfect. All right. Let's go ahead and do that. You can't read. Oh, it wants to know. Oh, sorry. Yeah. Min ancestor is going to be the. Sorry, guys, 1 second. Min ancestor is going to be the. Oh my God, why am I brain farting? I've done this question like a million times. It's the current node, or it's what you're comparing the node to. So let's say you're currently on the left side and you're at like 3 and you're comparing it to the current min ancestor, which would be in this case would be 14. That's your comparison. Oh man, I'm brain farting bad right now. Okay. This is what you're comparing the node to. Lowest ancestor in the tree for the current node. Yep. All right. What do you guys? Oh wait, hold on. I didn't even finish writing this. I tried to. Let me see if I can like adjust this kind of. If it starts to become a problem on my computer to where you guys can't read it and like the code also looks weird, then I'll move it to like something else. For now, we'll go with that. Oh yeah, that's how you do that. Cool. Yep. I need to use this website more. Ancestor. And then you add the legacy helper root pointing to right, comma, and perfect. All right. What do you guys think is next from there? You add them because you need to. It's essentially, think of this like the traversal. You need to get everything from the left and the right side. You gotta check for new ancestor. All right, let me see which one of you guys got this right. Viggy got it right. So after this, you don't really have to do like an else statement or anything like that. This statement should be good enough. but this is going to be what you return. Return. Do you guys understand why we do this? Got a few yeses. Anybody have any questions? Yeah, no, we all hate recursive coding. Don't worry, it's weird. Why don't we have to update to min ancestor? So okay. If the value of a current node is greater than the min ancestor, it means that the current node is greater than at least one ancestor. So here, I'll explain this from like the top, which is why we add the one. In this case, we're going to increment by one, then we'll recursively call legacy helper for the left and right side subtrees of the current node. Otherwise, we're going to call legacy helper again for the left and right subtrees of the current nodes. This update will be crucial as we need to compare the children nodes with their parent node, not with the min ancestor, as the current node itself is not greater than its ancestors. I did this earlier, so I kind of had to like think about it a bit, but that was essentially it. Min ancestor, what's the whole point of function? One sec. Int legacy count was we're making the helper function, yeah. So legacy helper is the helper function that we're making. Int legacy count, we're not using it. It's calling legacy helper. So we're making legacy helper. It's okay. It's probably been a long week for all of us studying for this thing. So it's a lot. Does anybody have any other questions, or would you guys like me to do another problem, or would you guys like to go on to the AVL trees? Another one? Okay. One moment. Okay. Give me just a sec. Was the problem we did first the BST or the binary tree question? The assign heights. I think that one was a binary tree question. I'd have to take a look at it again. Okay. Let me see if I could find another problem for us to do. I'm actually just going to do it off this website. Binary trees. I'll live code, or I'll live do this with you guys as well. All right. We can do this one, or I can skip this and do another one. It's fully up to you guys. Skip. All right. That's too easy. Yeah. All right. Let's see. Too much reading. I agree. Yeah. This is up to y'all. We can read through this, or we can skip the yap question. Yeah. I agree. Skip. Nah, no skip. All right, cool. We'll go through it. Just give me one moment. I'll give you guys. I'm gonna stop the timer for a sec. Can everybody read this first part of the question? Okay. Go ahead. I'm gonna give you guys about a minute or two to read this, and then we'll go ahead and try to solve it. I'd rather skip it on the actual exam. Not you're gonna have to read through the app because we get a bitwise question. You're reading like a 3-chapter book, bro. So you better get ready to read. Yeah, there are. You still got to read it though. Not read it all. Yeah.
Right here, right here.
Give you guys like a minute or two to read this. Which one is this from? Fall 2020? Can we get TTS? You got it. It's all you. You got it.
Section. A
little bit. This one was fall 2020, I believe. Oh, if y'all took, yeah, I'm sorry you took Sarkar. How was Sarkar CS1 actually? Kind of want to know now.
I need to talk for a second.
Hot take, fill the blank FE questions are worse than questions where you actually have to write the code. Yep. Nope, fully agree. I would root problem 9 return implemented.
So I
Probably.
Yeah, 4.0 is really fast, but who's going to use it in real world business applications that have a large amount of data?
So it's 9 is a key and key is not present. Yeah. Let me make sure I didn't okay. I'll go ahead and we'll stop this timer. We'll scroll down and then we'll see how we're gonna solve this. So let me go ahead and do this. Doing this. Nah, bro, it's fine. This is the correct reaction to having to take this exam, honestly. Okay. So I'll go ahead and read through the problem one more time, and then we'll go ahead and start the coding, right? So it says complete the function on the next page so that it takes the root of a binary search tree and an integer key. If key is in the tree, return the smallest integer in the BST that is strictly greater than that key. If key is not present or if there is no integer in the tree greater than key, simply return int min, which is defined in limits h. Your function must be iterative, not recursive, with a worst case runtime that does not exceed O of n. So you can't drop the elements into an array and sort them in order to solve them. You may assume the tree does not contain any duplicate values. However, root could be null. So here you got root is 18, it'll return 20. So you're looking for values strictly greater than the key. So if you traverse through the right side, you'll get 20. Seeing as how that's the only node there, that's your answer. And then for 9, 9 isn't even in the tree, so you'll just return it. All right. In your solution, you may make as man, I can't English right now. You may make a single call. Can I not English or can they not English? Okay. Took me a sec. All right. To either of the following functions. Assume they're already written and that they can have a worst case runtime of all event, right? So you have in find node, which takes the root of a binary search tree, possibly the root of a subtree with a larger BST, and returns the smallest value in that subtree. If that tree is empty, it returns int max. And then for int find max, takes the root of a binary search tree, possibly the root of a subtree within a larger BST, and returns the largest value in that subtree. If the tree is empty, it returns int min. An incomplete version of the function and node struct are provided on the following page, along with 10 blanks for you to fill in to complete the solution. Note that one of these blanks ought to be left blank and has been included so that part of the solution isn't giveaway. Thus, each blank is worth 1 point, and for at least one of 10 blanks, leaving it blank is the only way to get credit for it. So questions like this are a little bit harder. Just because you're not really coding it yourself, he has pre-code there, and you just need to pray to God that you get the correct line. So let's go ahead and pull up the IDE here, and then I'll set this up real quick. I don't know why this is like bugging me out. It is. It's fine. We'll just go through it. All right. So for this, what do you guys think it's going to be? I'm getting a lot of root. Okay. Well, unfortunately, not yet. Because here you're still initializing the parent. Yeah, it's going to be null. It is going to be null. This is evil. Yeah, I promise you it's evil. All right. And then as you, yeah, it's going to be null. So you're still needing to initialize the parent, and you'll see why. Again, I can explain this, but it's going to be better if you try to get this if statement right here, and you'll understand why. If that key is less than the root pointing to the data. You can do them in different ways, yeah. And just a heads up, the fill in the blank ones, honestly, yeah, I mean, I can't really say much to that. They just suck. But I want you to think you're gonna see why we set that. Would you access root left keys less than? Yes, that's part of it. Can you tell me how you would do that? Exactly. There you go. Does this make sense now? What is the second one? Yep, Viggy's correct. Root is equal to root pointing to left. So if that key is less than that root data, we set that parent to the root, and then we'll traverse the left side. All right. So we have that case done. Now we have the else if of whether the key is actually greater than that root data. What do you guys think we're going to do? You do not set parent to root on both. Yeah. Root is equal to root right. Yep. Perfect, guys. Now remember how they said there is a root is equal to root pointing right. So we'll traverse the right side. Remember how they said there's going to be a blank line somewhere in this code? Why do we not set parent to root on both? I'm trying to think of the best way to word this for you right now. But essentially, give me one sec. I'm still trying to figure out the best way to explain this. I'm also doing this with you guys technically right now, so I didn't prepare some of these questions. Essentially. Beatrice got it right. That's essentially why. It's weird. It's extremely weird, but one of the other things is we're going to be leaving this blank because all you really need to do for this is traverse the right side to find that value. Yep. So in the problem, you remember how yeah, giving a blank line. Yeah, he said there's going to be a section where there's going to be a blank line. So an incomplete version of note that one of these blanks ought to be left blank and has been included so that part of the solution isn't given away. Yeah, they're going to do stuff like this if you see it on the test. You may or may not, or one of the professors may or may not. Just look out for that and make sure that you read it because you don't want to lose points for something like that. Okay. All right. Yeah, blank line is a good. I'm like 90% sure he wrote this question. So yeah. All right. So we're gonna move over to the. Am I missing? No, I'm not missing anything. Okay. This next if statement, right? So what is the next condition you guys think we need to check? Can we see the question? Yeah. Okay. That is equal to key. Not necessarily. If what else it's equal. Um, kinda. 1 second. If it's not greater than it, not less, it has to be equal. I'll give you guys. I'll give you guys a statement. See if you guys will understand from here. So for this one, we're actually going to check to see if the root right does not equal that. If that root right, yep, does not equal null. And then what happens if the parent is null? Or the parent does not equal null, sorry. Perfect. Why are we using find min? So we're trying to find, yeah, the minimum number that's greater than the root. Okay. We return the parent data. What's the else statement down here? Int min. Okay. Cool. Be int min. Because none of them passed, then we got to return int min. And then what about this one? Cool. All right. This question's a little bit weird because it's fill in the blank and we don't really have our own kind of implementation for this. You just kind of need to go based off of what they give. But I'll go ahead and show you guys. Can you guys see it? Or should I zoom in? The last return answer is going to be the return int min. Unfortunately, I can't make it harder. Yeah, unfortunately, guys, I'm gonna have to move on to AVL trees after this because we're kind of like short on time. So we got to get through like a decent amount of it. If we have more time at the end and you guys, yeah, I know. If we have more time at the end and you guys want to look at more binary tree questions, we can do more. We just have to wait until we finish everything else, okay? So I'll go ahead and move on to the AVL trees. So real quick, how do we feel about AVL trees? How does everybody feel about AVL trees? Because before I go into it, if you feel like you're good and everybody here feels decent with it, I can just go into the questions, see how you guys feel, and then we'll move on to sorting. Go into questions? Okay. Will AVL trees always be tracing? Not always. Yes, honestly, I haven't seen a coding AVL tree yet. And then here are my
Yo,
Yep.
just for the sake of the recording, just go over the slides just for the people that aren't here.
Just for the people? Yeah, I got it.
Yeah,
We'll go through it. We'll go through the base of it though.
Gotcha.
Okay. So we'll go ahead and talk about AVL trees, guys. So an AVL tree is defined as a self-balancing binary search tree where the difference between heights of left and right subtrees for any node cannot be more than one. All right. So the AVL tree to our right is actually a AVL tree because the difference between the heights of left and right subtrees for every node are less than or equal to one. All right. Go ahead and move on to the next, right? So the difference between an unbalanced or a balanced and an unbalanced AVL tree, right? So like I said earlier, the differences between the heights of the left and right subtrees for every node is less than or equal to one. So the one on the right is an AVL tree, but if you see the one on the left, yeah, the differences here would be one, but if you look at the level beneath, there's an extra node, which isn't allowed in an AVL tree. Okay, so we'll go ahead and talk about the rotations. This is going to be a left rotation. If we have a right unbalanced tree, so we have a right heavy tree, we'll go ahead and perform that left rotation. We rotate on B. Well, we rotate on A, but then A goes to the left and then B, A, C. And then we have our right rotation, where if a node is added to the left subtree of the and oh man, I messed up the wording on this, but the AVL tree may get out of balance. We do a single right rotation. So if we only had A, B, that's fine. But then if we add C, now A is too heavy, we rotate to the right. And then we get B, C, A. A becomes the right child, C becomes the left. A left-right rotation is a combination in which the first left rotation takes place after the right rotation executes. So if we have C, A, B, so a case like this, we would rotate B into A's position, A into B's. We'll get a straight line like this, and then we'll do one more rotation on C, which allows us to get to this point. I can't see chat at the moment. So if you guys have any questions, I'll go ahead and answer them to the best of my ability once we get to the part where we talk about the questions, okay? So we have the right-left rotation. A right-left rotation is a combination in which first right rotation takes place after the left rotation executes. So similar to the other one, but in reverse. Sorry, guys, I'm but let's see. Okay. So that's what we had for the AVL trees. However, I think I had prepped problems on here for us to do. The double rotation occurs. All right, let me see. If you just explain double rotations. Oh, the kicker rotation. Rotation. Okay, so I'm gonna be okay. Lewin answered that. I'm gonna be able to answer those by just doing this problem, or the problems that I have set up for you guys. So this is the FE that I just took. The only thing is, let me see. I really wish I didn't forget my mouse. Nope. What was the command again for to draw?
Hit Shift L, but that only works on Google Slides. Like it's a Google Slide command. I'm not sure.
Oh yeah.
If you were.
I know you could do the annotate. There you go. Maybe. Yeah. Yep.
There you go.
I'm gonna move over to the room, right?
Yeah. Oh. Go.
I got some.
All right. Let's see. Spring FE went wild. That permutations kind of took me out too. I'm not gonna lie to you. We'll go ahead and do it. Oh wait, hold on. I have so much on the screen right now. It's insane. Go ahead and we'll zoom in. So show the final results of inserting 48 into the AVL tree below, right? So we want to insert 48. 48 will go here, right? And we notice, honestly, it's times like this where I wish I still had an iPad. But unfortunately, I don't. All right. I like permutations. Yeah, that's a very unpopular opinion. Okay, so for here, we want to insert 48 into the tree, and we notice that the tree is currently imbalanced, right? So, and that the biggest imbalance is going to take place from here. So what rotation do you guys think we're going to do for this? The first rotation, at the very least. Okay, so I'm getting it right. Okay, so I'm gonna go ahead and do this real quick. So we're inserting 48 and we're heavy here. We're very left heavy at the moment, and we want to go ahead and do a rotation. We're actually going to be doing this for the first rotation. So 50 remains there. So, all right, 50 remains there. We're actually going to have 37 here. Bear with me with like the drawing because this low key suck. Like doing it on a touchpad. Fortunately, I forgot my mouse. 25 goes here. We believe in your skill. Thank you. I'll try. 25. We have 12. Oh, that's so. Just know that this is 12, all right? And then we got 18. Why not just type the numbers? Honestly, that might actually be a worse time. Do that. 12, 18 would go here. Do that. All right. So whenever you do a rotation, right? And similar to that, the rotation that I talked about where we have the straight line at this point, And 37 becomes the note. We're gonna go ahead and do, we'll keep it 45 and then 48. Because 25 becomes the left child of 37, this is gonna be so bad. It's okay. So because this becomes the left child, you lose 36, right? But all you're really gonna do is traverse it down the tree. You get to 25, and you put 36 here. And then you follow that same rule with anything that you want to replace a child with. Any replacement you do, you have to follow that rule. You just traverse it down the tree once it becomes once you have a new side that becomes a child of something else. So this is going to be the first rotation, right? We'll have 50, 80, 90, 37, 25, 12, 18. Oh my God, I couldn't even read it. And 36. And then we have 45 and 48, right? So we still have to do another rotation, right? Because it's still left heavy. Where do you guys think we're going to rotate towards? Right at 50? Perfect. There you go. So 37 becomes the head. However, 37 is gaining new children from here. So what do you think we're going to do with that 45 and the 48? Put it on the left. It becomes perfect. There we go. Good job, guys. Yeah. So I'll explain it. Can't this be done in one rotation? Not really. You still have to. So right now, the biggest imbalance is coming from here on the first rotation. It becomes right heavy when you do that, and then at that point, it's a problem. So you need to do the first rotation, and then you'll be able to do your second rotation, and then boom, right? Just remember that whenever something becomes the new child, you have to traverse the old children down the tree. Yep. What? 50, 37. I don't think that copy and pasted right. But for the most part, if I just type, we could actually just type this. The final tree is black text. It's blue, but we can do. Can we take a bathroom break soonish? We most definitely can. It'll be very quick and brief though. It'll have to be quick and brief. So this will be 37. And then from here, we got 25, 50. Wow, this is a lot harder to type it. Okay, so your children, yeah, that's still, can we take a bath? Okay, 37, 25, 12, 18, 37, 36, 45. That's still gonna be on the, no, not the 45, 48. Sorry about that. So 45, 48 will actually be the new left children of 50. Because remember, it's gonna start traversing down the tree. Once you remove it, it has to traverse. So we'll do 45, 48, just plainly. It'll be a lot better. Yep, there you go. That's a better representation of it, kind of. But if you insert into left subtrees, why are you rotating? One more, guys. Insert into left subtree. Where are you rotating left on the first? So whenever you're calculating like the weight of a node, right? Leaf nodes are usually going to be 0. So down here it'd be 0, 0, 0, and so on, right? And then you'll move up, and then you'll have your one. So you'll have your, yeah, I understand the height part. Okay, so we rotate it. So we'll rotate left because that first right rotation, if we do that right rotation, right? Me trying to find a way to explain this as best as I can. But if we do that first right rotation, it's going to make it way too heavy on the right side. And then you'll have to do way more like rotations at that point just to get to where you need to go. But it'll keep the tree unbalanced if you keep doing that. Essentially, sometimes, but not really. It's weird, but let me see. Give me a few and I'll have a better explanation for that for you. But for now, I have to move on because I think I took way too much time on the binary tree section. So I have to push through. One slide. I think this was the other one right here that I had. Yeah, this is the other one that I had planned for. Go ahead and erase all this. All right. For this AVL tree, what do you got? We're going ahead and deleting 8 here. What do you guys think the tree is going to look like after the first rebalance? So we're removing 8 for this one. If we remove 8, what's the first rotation going to be? Yep. That left subtree of 27 is going to be 18, 15, 23. Yep. Okay. So it is going to be the same subtree, just the difference is 18, 15, 23. I'm going to do very minimal drawings, unfortunately, because I don't have my mouse. Oh, that's perfect. Ron, you see the chat? Yep. That's okay. So that's the main one. Okay, so that's going to be the first rebalance. What do you guys think the second rebalance is going to be? $46 to the head. Wouldn't be 46 to the head. So what do you guys think happens to the tree after that rebalance? Yep. 49 does become the root. The left rotation. 49. I'll draw this out just so you guys are able to see it. 60. Just know if they ask an AVL question, more than half the time they're just gonna have you rebalance it. Ten-point ABL question. Yeah, we just gotta pray that this is a 10-pointer. Or if they add an ABL. But prepare for the possibility of there being a try. $46 will go here. This will be 35. Oh, let's see it. I think he probably got in the shot. 27, 23. Oh. $18 is gonna have 15 and 23. It was essentially that you were just missing the left subtree. Yeah. Yeah, you just flipped the 18. So 18, 15, 23. Then you have your 46, 35, 27, 49, 60, 53, 58, and then 70 down here. All right. I would draw this a lot better, but unfortunately I forgot my mouse, so touchpad is all we got. As for any of the ABL questions, go ahead and leave them in the chat and I'll get to them as soon as I can. I just have to keep pushing forward. I was told that do you guys need a bathroom break? They have not sent the FE emails yet. Okay, go ahead and I can pause this for about 5 minutes. You guys are good. Go ahead and take a bathroom break. We'll go ahead and start up again at 3:25. All right, guys, can everybody hear me? Okay, cool. So we're gonna go ahead and get into sorting. Unfortunately, I took up a decent amount of the time, so I'm gonna have to go through this. Whatever questions you guys have, I will answer as soon as I get through my section, okay? We're just gonna get through this and get through some of these questions, and then again, whatever questions, just throw them in chat. We'll take care of it. All right. So we'll go ahead and start with insertion sort, right? So we have the steps to achieve insertion sort. Number one, we're going to have to start with the second element of the array as first element in the array is assumed to be sorted, right? So in this case, if you look at our first pass, we're making 23 our sorted array, while the rest of it is going to be unsorted. Step two would be to compare the second element with the first element and check if the second element is smaller, then swap them. If you see here, 23 is in our sorted array, 1 is in our unsorted, and we're comparing 1 with 23. Since 1 is less than 23, we shift 23 to the right. We place 1 in the section in 23's previous element, and then we continue on. And that's it, honestly. That's insertion sort. Move for the third step, you're going to move to the third element, compare it with the second element, then the first element, swap as necessary to put it in the correct position, and you continue this process until it is completely sorted. So in the third pass, we have 10. 10 is less than 23 but greater than 1, so we place 10 in between 1 and 23, increment 23 by 1. Check 5, then check 2, and so on and so forth until it is sorted. Worst and average case runtime for this is going to be O of n squared, with the best case runtime being O of n. Selection sort. What is it? The algorithm essentially repeatedly selects the smallest or largest element from the unsorted portion of the list and swaps it with the first element of the unsorted part. I'm going to say this from now. If we get a selection sort question on the exam, please read the question, because they may ask you to either do max or min. If they tell you the min value, it needs to be sorted by the most minimum value and so forth. If it's max, it's got to be the max. So here, I believe we're doing it by the minimum element. So we start with checking out 2, and 2 is currently, why am I brain this? No, so yeah, we start with 2. We check the array to check for the correct position, and we place 2 in the position of 7. 7 is going to be placed in the last element. Now we're checking, wait, hold on, is this doing, yep, then we check 4. 4 is going to be checked with 5, and then it'll swap the positions. Then 5 is going to be checked, it's the next minimum element with 7, it's in the correct spot. Life is good, 2, 4, 5, 7. So for this scenario, we're doing it with the min element. The most of the time I've seen them do max element, just know that you can do it with the minimum element. So you take the most minimum one and you just keep placing it where you need to place it. That's essentially what this is. Bubble sort. Bubble sort is the simplest sorting algorithm that works by repeatedly swapping the adjacent elements if they are in the wrong order. This algorithm is not suitable for large data sets, as its average and worst time complexity is quite high. The best case runtime is O of n. O of n squared is the worst and average. The initial unsorted array. So we start by comparing 5 and 3. And because 3 is less than 5, we swap it, and we just keep doing that until the elements are in their correct positions. So you're essentially trying to find the largest element when you're doing your swaps. Once the largest element is found, you just keep moving that down the elements of the array. So here you can see we stopped when 5 is less than 8. And we start doing the check of if 8 is greater than 4. 8 is greater than 4, then we move forward. 8 is greater than 6, then we move forward, and then 8 is in the correct position. And then you would repeat the same steps, 1 through 5, until there's no more swaps required. So essentially for the next one, we would go back, we would check 3 and 5. 3 is in the correct position. We would then check 5 and 4. 5 and 4 are not in the correct position. They swap. 5 and 6 are in the correct position. Boom, life is good. Sorted array, and it'll just keep doing it until everything has been checked. Merge sort, the wonderful sort that we all hate, right? What is it? Merge sort is a sorting algorithm that follows the divide and conquer approach. It is a recursive sort. So It's essentially dividing the input array into smaller subarrays and sorting those subarrays, then merging them back together to obtain the sorted array. Here's a step-by-step explanation of how it works. Divide is essentially divide the list or array recursively into two halves until it cannot be divided anymore. Conquer, each subarray is sorted individually using the merge sort algorithm. Merge, then the sorted subarrays are merged back together in sorted order. The process continues until all elements from both subarrays have been merged. I have an example to the right. You can see how it is split down completely, merged, and then merged back together to create the sorted array. Quicksort. It is another divide and conquer algorithm that picks an element as the pivot and partitions the given array around that picked pivot by placing the pivot in its correct position in the sorted array. Just a heads up, when it comes to the pivot, more than half the time, they will tell you what they want you to use as the pivot. Otherwise, you are free to use whatever you would like as the pivot in any of the problems, all right? The key process in quicksort is the partition. The target of partitions is to place the pivot. Any element can be chosen as the pivot as its correct position in the sorted array and put all the elements to the left of the pivot and all greater elements to the right of that pivot. Partition is done recursively on each side of the pivot after the pivot is placed in its correct position, and this finally sorts the array. So if you look at the example to the right, it uses 13 as the pivot. So it checks the array for all values that are less than or equal to 13, puts it on the left, and all values that are greater than 13 puts it on the right. And then you just keep picking that pivot until finally you get down there, and then boom, everything is sorted. All right. So we got problems here. Again, I am going to be moving through these a little bit. If you have any questions for these, I will get to them as soon as we start the other sections. Just leave them in chat and I'll take care of it, okay? But for now, we're going to start here. All right. So for this question, we're going to complete the following merge function that is used as part of the merge sort process. I think I could just do that. Yeah, there we go. The function performs the merge operation from left to mid and mid plus one to the right index of the array. All right. So they essentially created the merge function for us, and we just need to complete the remaining part of the code that will merge the left and right arrays into the array. Okay. So I'm going to go ahead and start coding this up. So we'll do while I is less than n1 or j is less than n2. Okay, this loop is going to continue while we're still traversing I and traversing j. Here we have I is equal to 0. That's the initial index of the left subarray. J is equal to the right of the subarray. And then this is the initial index of the merge subarray. And then, sorry, this is how this works. And also, if you guys have any other questions on any of the code, let me know later, and then I could show you guys, but we got to get through everything. All right, so this continues until I reaches the end of the left subarray. Same can be said with J. I know I spelled that wrong. We're going to do the check if J is equal to N2, meaning we've traversed J, or I is less than N1, and the left subarray index is less than the right. This essentially checks if right index has been traversed or if the current element in left subarray is smaller than the current elements in the right. If this is the case, populate the left subarray values into the sorted array. So we'll have array of k is equal to left I, and then we increment I to keep going through. Otherwise, we'll do array of k is equal to the right, essentially the opposite of the previous case. We'll increment j, and we'll continue, and then we have to increment k because k is in our merged array, and we need to be able to place the values, right? So we'll increment k. Pivot can be random. Pivot can be random, yes. K plus plus. Boom. This will be easier if I do it on the 90E, but this is how it's going to be for now, okay? Anybody have any questions about this? Show the solution as well. That way you guys can see like how it's graded. Assuming you get this, like just doing this and this, 2, 4, 5 points. You get half your points by just doing this little bit of logic down here. Okay. I'll go ahead and do the insertion sort problem next. All right. Insertion sort is going to work exactly how I said before. So show the results after each iteration of performing the insertion sort on the array below, right? So we have 16, 3, 18, 15, 1, 8, 12, 4. So it chose 16, which these were 10 points. Yeah, me too, don't worry. We're going to go ahead and start with the first line of 16 being our merged array. This is going to be our merged. This is our this is our sorted. This is our unsorted array. So we insert 3 and we notice that 3 is less than 16. So we place 3 in front of 16. Then we have 18, 15, 1, 8, 12, 4. So for the second iteration, we're going to actually insert 18. 18 is going to be greater than 16. So this is going to remain the same for the second iteration. So we got 3, 16, 18. For the next iteration, we're going to insert 15. 15 is less than 18 and less than 16, but greater than 3. So we'll do 3, 15, 16, 18, and then we keep everything the same, right? 1, 8, 12, 4. All right, next iteration, we're inserting 1, right? So we'll go ahead and insert 1. 1 is less than everything in our sorted array currently. So we got 1, 3, 15, 16, 18. And then we have 8, 12, 4. Right? Next, we're going to insert 8. 8 is going to be less than all of these, greater than 3. So we're going to have 1, 3, 8, 15, 16, 18, 12, 4. The next iteration is going to be, we're inserting 12, 1, 3, 8, 12. This process is going to keep continuing until we have the sorted array. 16, 18, 4, and then 4 being the last element. I'm just going to do this for the sake of time. We'll replace put 4 here. Anybody have any questions for this? Or was this kind of like self-explanatory? Yep. Essentially, yeah. All right. I'll go ahead and move on to the next question. My thing will let me. Yeah. Next one is going to be a selection. So beauty of recursion. There's no beauty in recursion. Okay. So for this one, I want you guys to pay attention to one thing. where we select for the maximum element in each iteration. So we're going to be performing the selection sort where we select for the maximum element in each iteration. So remember how I said that sometimes they will specify what they want you to use. For this one, it's going to be the maximum. If you look here, we have 13, 11, 9, 16, 12, 15, 10, and 5. So I'll go ahead and copy this. And then for the next one, we have 13, 11, 9, 5, 12, 15, 10, and 16. So we started with grabbing 16 and we put it in the correct position. Now our next one, our next biggest element is going to be 15. So we have 13, 11, 9, 5, 12, 15, 10, and 16. Because 15 is greater than 10, that's going to be the next iteration. From there, our next largest element is 13. 13 and 10 are going to swap places. Yeah, 13 and 10 are going to swap places. So if it was min, we would swap 5 to the front, yes. You always, so depending on what they ask you to start with is what you're going to do. So we'll do 10. One moment. So this is going to be the next iteration, that 13, 15, and 16. All right. Oh, I really need to understand how this works. Okay. So then from there, we have 13, 11, 9, 5, 12, 10, 15, and 16. Did I just rewrite them? I did. Sorry, I lost count on my iteration. This was iteration 2, so we're on iteration 3. So from there, it's actually going to do this. 10 is actually going to take the place here. We'll do 13, comma, 15, comma, 16. Sorry, I lost my place on that iteration. And then from there, we have 10, 11, 9, 5, 12, 13, 15, and 16. Because the next largest to that, to 13, is going to be 12. And because 12 remains in the same spot, since it's less than 13 but greater than 5, then we keep it in the same spot. Make sure that if it remains in the same spot, you write the exact same thing. Don't just skip that and continue writing on the other iterations, okay? Then from there, we got 10, 5, 9, 11, 12, 13, 15, 16. And then we continue with this. We get 9, 5, 10, 11, 12, 13, 15, and 16. And then finally, the last iteration would just be the sorted list that we have at the bottom that they provided. Any questions about this one? No? Okay, cool. So if time allows, after we get through the math section, let me know if you guys want to do any other questions that aren't related to math, and then we'll go from there, okay? So I'll go ahead and pass this on to Lewin. Whenever he's ready.
All right. Here, am I co-host on this or not?
Not yet. Let me change
Yeah.
that.
So I don't think I can share my screen unless, or maybe I can. All right.
Does that work?
That's the other limit. I'm on my computer and my iPad. I need both. Oh wait.
Let's see.
Okay.
Where's the other Lewin? Got you.
Nice. Okay. Right. Share content. It's loading. All right. Can everyone see my screen?
Yeah, we can see you good.
All right, dope. All right, so starting with algorithm analysis, 1 and 2. This is both sections. But all right, so the first thing, or two things that we want to look for when analyzing an algorithm are runtime and memory usage. But like for this specific exam, we only need to worry about runtime. And since in cases of runtime, there's so many different factors that like change the runtime of an algorithm, we have derived a notation to just like refer to it generally or estimate the runtime by just looking at the code and then deriving it from there. And that is big O notation. So some things about big O notation is that it's really simplified. So some steps to evaluate it would be like when you look at it, you could have like the term, like in terms of n, your runtime be a very complicated equation. But in big O, a lot of that is just going to be irrelevant to the actual runtime of it. So let's say you have any constant factors in your notation for big O, or you have any terms that lose its significance as n becomes larger in big O, those are all just going to be irrelevant. So let's say something like 4n squared plus 3n minus 5. So immediately here we notice that we have like -5 here. That's a constant. It's going to be irrelevant in the terms of the notation, especially as the equation gets larger. By the way, can everyone see like my markings? Is this good?
Yep, it looks good.
All right, great. So so that is automatically going to be irrelevant. 3n, now 3 has an n, so it's not just a constant. But because we have this 4n squared, this 3n is also going to be irrelevant as the equation gets bigger because the n squared is so much bigger than the 3n. So we also don't care about that. And then this 4 is also a constant, so we also don't care about that. So this really just evaluates out to O of n squared when you're looking at it. And then another thing about big O is that it normally by default is going to be the worst case or the upper bound of the runtime, but you're also going to be asked about like the best and the average case. So there's different notations for those. I've never seen them ask for the notations on FE. It's just always going to be big O and then give the best and average worst case runtimes, but be mindful of average and best because it's not always just going to be the worst case that you're asked for. Some limitations of big O is that it's not really useful for like small input sizes. It doesn't really tell you anything, and it doesn't look for memory or care about memory. And then moving on to, so let's say we're looking at a piece of code and we want to like evaluate its runtime. So, I mean, the first thing you want to look for is going to be see if we can find any loops. So in this specific example, we see one loop already. And then inside the loop, you want to see if there's like any specific operations that will increase the runtime. So we can see that in our loop. So our first loop, we know it's going to run all the way till n, and we want this in terms of n. So we know this is going to go. This is going to go until n. So we know this loop is going to run n times. So from like 1, 2, 3 to n, we're going to do what the operation that is in this loop. So every time we run this loop, we're also going to do another loop because that's inside the operation for this loop. And this is going to run for every iteration, we're going to run the same thing. And this is going to run for every time this loop runs. So from just specifically that, we know that we're running this n times. For every n, we're going to be running another operation n times. So we can derive that this code is O of n times n, or O of n squared. That'd be an example of how to do it. So you want to look for any loops and then look for any operations inside or outside the loops. So let's say if this loop was outside, then we just have two O of n operations, and it would be a 2n, and we know that that constant at the start doesn't matter, so it'd just be O of n. Or if we had like any operations inside that were O of 1, those would also not matter because we have our O of n loop operation, and those would all just reduce out of our big O operation. Okay, moving on. So another thing, so you're not always going to be asked to like just trace an algorithm and get the O of n runtime. Sometimes you're going to need to, they're going to give you specific values, such as the runtime of an algorithm, or like the constant, or the like actual big O notation of the algorithm. And then you're going to need to plug it in to this specific equation, and then solve for the thing that you're not given, and then use that to solve the rest of the equations they give you. So it's basically just algebra with some like runtime notation that you need to understand. So it's like if you get like the runtime of something, and we know it's like 500 milliseconds, and we know this is equal to c, where c is some like constant, times our big O runtime notation, or f of n, which could be anything. They could give you like n squared, 2 to the n, log n, n to the 1.5, whatever that is. You would just then like plug that in, and then you would take n, which is the number of operations, and you would multiply it by whatever your like runtime is. So if it was like log n, then you would just, you know, take the log and plug in that value, whether it be like 1000 or, and then yeah, you would just evaluate it there, solve for c, and then take that c and plug it into whatever you need to solve the rest of the equation. All right, and then I'm just gonna do some problems to demonstrate that. All right, so to start, this is a just a like we just gonna trace this one and then see what the big O notation is here. So does anyone notice anything in specific that, oh yeah, I have not been reading the chat. Okay. Yeah, n squared. Nice. All right. Yeah. So has anyone been reading, has anyone noticed anything in specific that we need to like look at first? Anything that jumps out in this code? Divided by 2, yeah. But like before that, like any loop? Yeah, a while loop. Thanks. All right, so there's a while loop. So we have a while loop. So now we shut up. Yeah, so now we want to evaluate anything. We want to know how long this while loop is going to run, and we want that in terms of n, quote unquote. So we know this while loop is going to run while the while jump is greater than 0. So we know our last iteration of this is going to be when jump is less or is 1. That's the last iteration of this, or last possible iteration of this. And we know that jump starts at n divided by 2. So now we look for like any other operations that take any significant runtime inside the loop. Does anyone see anything? No, yeah, because there's nothing to see, so that's good. So yeah, so we just take we know what our jump starts at. So our jump starts at, oh shoot, you're right, at n divided by 2, and then we divide that by so our n divided by 2, and then like you guys mentioned earlier, we have our we notice that our jump is divided by 2 for every iteration. So we know that our jump is going to be divided by 2 k times, where k is the number of times the loop runs, right? And then we know that the last value that runs is going to be 1, or that's like that's our base right there, because as soon as it hits 0, we're not running the loop anymore. So we take this, and then we just want to solve for k. So we can go ahead and evaluate that this comes out to 2 to the k. And then this evaluates out to, I believe, like, here, let me flip it around. Yeah, so this is basically, from here, it's just algebra. So it's from k is equal to log base 2, because we want to isolate the k, so we get rid of that exponent with the logarithm, and it's a log base 2 n divided by 2, and that's what k equates out to. And then, we take our big O. We can ignore this n divided by 2 because it's irrelevant in the scheme of the runtime. And so, yeah, this basically just reduces to O of log n. And yeah, that's the runtime of this algorithm. Now I saw, yeah, my bad for the handwriting. Okay, so the n divided by 2 over 2 to the k. So the n divided by 2 is because our jump starts at n divided by 2. Okay, yeah. So I'll get to you, Caitlin, in 1 second. So our jump starts at n divided by 2, and we know it gets divided by 2 k times. And so that's where that comes from. And then from there, we just want to evaluate for this k to find our runtime, because and to find our runtime in terms of n. So if you know the answer, so like a lot of people could probably just look at this, right, and know that the answer is log of n. And that's completely fine. If you can just do that, you can put that down and get full credit. But like, if you want to, like, if you're not sure and you want to like try to get some partial credit, if you show some math or some reasoning, then you can get like some points on this, even if your runtime is wrong. But if you see this and you're like, oh yeah, it's log of n, I can tell that immediately, then just write that down. Don't waste any more time and just move on. But how could you elaborate on, Dev, on what you mean? Okay. K is just arbitrary. You could really call it anything. You just need to. Oh, okay, I got you. Yes. You don't need a show work if you recognize it right away. Yes. Yeah. All right. Okay, I'm gonna move on to the next problem. In case anyone has any more questions, just drop them in the chat. Okay. All right. So this is the other kind that you could get. So for this one, notice how they're giving you like specific values. Let me pull it up here. Okay. Yeah. So for this one, they're giving you specific values. So this is our equation. So it's T of n is going to be equal to, so this is what you want, like you want to memorize T of n is equal to C times big O of F of n. F of n is going to be given as well. So our F of n here is n log m. That's one of the values they give us. N is the data sets, m is our values. And so that's one of the things we plug in. And another thing we plug in is the runtime that they give us, which is 500 milliseconds. So here we go ahead and plug in 500 milliseconds is equal to C, which is what we're going to solve for, times big O of n log n. And then we know that we're also given our n, because we know our n is data sets. So can I get rid of this? Yeah. So this is our n, because it's 100,000 data sets with 2 to the 16 values. Okay. So we plug that in as well, and we get, let me see if I can make my writing a bit smaller. All right. Yeah, so we get 500 milliseconds is equal to C times, and then this is going to be what, just n is 100,000 times log of 2 to the 16. 16. Okay. And then, all right, so quick math lesson. Basically, from after you get to that point, it's just algebra. So you just do algebra. I don't know if you don't remember algebra, start making things up because maybe you'll get partial. But yeah, from here it's just algebra. So quick math lesson. If you have a logarithm that's like log of a to the n times b to the m, it's going to be equal. That's always going to be equal to m over n times log a to b. So yeah, taking that, we can go back and we can derive that our like 16 or log 2 to the 16 is going to equate out to 16 log 2. If you don't know if like your log isn't given a base, it's just log base 10. That's like the default, which has it's to the power of 1. So it's just 16 log 2 here. And yeah, so it's 16 log 2. And then to like isolate for the C, we know that our C is going to be, we just divide the whole thing by 100,000 times 16 log 2. And we get that our C is equal to milliseconds over 1,000, 16, 2. And then yeah, that's our C from here. Is anyone confused on how I got there?
I'd put a multiplication sign between the 100,000 and 16 because it kind of looks like it's like, what is that, 10 billion 16?
Yeah,
There you go.
All right. Yeah, my handwriting is terrible, by the way. So no, you don't get that on a formula sheet. You just got to know that. If you don't know that, then, yeah. Yeah. But as everyone know how I got there? Okay. So that's our C. And then we can like simplify this by just dividing 100,000 by 500. It's like, just simplifying fractions, and we get this evaluates to, I believe, would be 1 over 200 times 16 log 2. And then 16 times 200 is going to evaluate to 3,200. So this is equal to 1 over 3,200 log 2. And that's the value of our C. So now we can take the rest of the equation or the problem. So given this information, how many milliseconds would we expect the program to take to process 60,000 data sets, each with 2 to the 20 values? So now we're still given our data sets, we're still given our values, but now we want to find how many milliseconds it takes. So we have our C, we have our data sets and values. So we just plug in the C and then solve for the runtime. So we take our C and we like set up our equation. Just gonna scroll down here. It's 2. I'm gonna leave myself some room. Equal, and so it's 1 over 3,200 log 2. And then that is times is our whatever data sets 60,000 this time. And log is it 2 to the 20. All right, so same trick we did last time. We can go ahead and move that 20 to the front and have it be 20 log 2. And then yeah, that will go. All right, And then so now again, you're just simplifying this here. Any questions? Yeah, okay, no, not so far. Oh yeah, so now again, you're just simplifying. So yeah, it'll be easier if I like write out the entire fraction. So it's basically 60,000 times, and this is millisecond, 60,000 times 20 times log 2 over 3,200 times log 2. And then from here, we can go ahead and start simplifying things. So we know that the log 2 gets dropped. We know that we can divide our 3,200 by 20. And just assume I can do that in my head. But yeah, that is 160. And then we keep the 60,000 at the top. And then the 20 reduces to 1 because, you know, we were divided it by 3,200. And then we have 160 at the bottom. And then we still have our millisecond, the times 1 millisecond from up here. And we move that here. And then this reduces to, because I can also do that in my head, to 3,000 milliseconds over 8. And because I'm so good at mental math, this reduces to 375 milliseconds, which would be our final answer. Any question? If you can just do long division for all of that. I wasn't gonna do long division like right now, but yeah, if you aren't great at mental math, just go ahead and write it out. Any question? None? All right, so that's basically it for algo analysis 1 and 2. Moving on to everybody's favorite summations. Summations are basically a really good tool for evaluating series or sequences that have a lot of adding up numbers or sometimes multiplying numbers, but which I have seen before, but I wouldn't worry about it too much because as you'll see, they only give you the closed forms for like addition summations. So if basically what you're gonna do when you see a summation is you're gonna like manipulate the values to try to get it to one of these forms. And that way you can just like plug in the values n y's and then do some algebra to evaluate the entire summation. So like, let's say if I had c to the n, like I had n i's equal to 1 and it's c to the n, like this is already in that form, so I would just be able to, or it isn't in that form, but like let's say c is a constant, so I would be able to like take out the c because it is a constant and just multiply the summation by the c, and then now the summation is in a form to where I can just plug in the n, even though this is n, this would be I, but yeah, so I could just plug in the n because that's a closed form and I would have it equal to c to the n. All right. And then so the way, some techniques that are going to help you like manipulate summations around, let me check for questions. There's one that's left out, I think. Yeah, there is. It's for geometric series, which I'm gonna get to. I don't know why it wasn't on the formula sheet. I guess we'll just have to like memorize it. But yeah. So here you can shift the index of a summation. Yeah. So you can shift the index of a summation by so whatever you add to the summation, you would have, or whatever you add to the index, you also have to add to both bounds, and then you do the opposite of that to the closed form of, not the closed form, to the form of the summation. So if I'm like, for example, if you take k equals 1, and so if you have like k is equal to a and b is equal to a, and then you then you add 1, then you have to like subtract 1 from the inside, and then same thing here. So okay, yeah, sorry, bad explanation, right? So if you have b and then k is equal to a, if you were to subtract minus a plus 1 here, you would get to like 1, and then you get to b minus a plus 1, and then you would do the opposite of that in here, which is a minus 1. And if you were to subtract just a, so if you were to do a minus a, then you would do minus a to the upper bound as well. You would get 0 here because a minus a is 0, and then you add a to the inside of the summation. This makes sense. Okay. Then you could also split your summation. So if you have 2 different forms being added together, you can split them into 2 separate summations. That way you can evaluate those closed forms separately, and then you can add them together. Or you could also split the bounds of a summation. So let's say if you have like some summation that goes from like 0 to 10, this would be equivalent to the summation of or let's say the summation goes from 3 to 10. This would be equivalent of the summation that goes from 0 to 10 minus the summation that goes from what is it? Would it be 3 to 10? Yeah. No, yes, this goes from 3 to 10. So that would be minus the summation that goes from 0 to 3. No, you have to do the 0 to you have to do the middle step for the index shift. Yeah. Oh wait, I see what you're saying. Yeah, this isn't like a separate, these are separate steps. So this middle one here is if you're adding if you're adding a plus 1 to the to your bounds, and then this other step is if you're adding just a. So these are just 2 separate examples. But yeah,
the reason you want to do that is because some formulas, they have to make sure that the bottom bound is 1, and others need it to be 0. So like, for example, if you have that first equation on the left, and I think a geometric sum starts at 0, I don't know, but like certain formulas, I have to brush up myself, admittedly.
yeah.
They have to start at 1 or at 0. So basically that's just showing you, A, you can shift it to 1 by doing b minus a plus 1, or you can shift it to 0 by just doing b minus a and leaving it as is, because it depends on really the situation you're in and what type of formula you want to use.
I on last one index instead of k. I would assume that's just arbitrary. Wait. Yeah, it's a good question. Why is that high? I don't know why the bound changed.
That's probably just a typo. Hang on.
Yeah, I wouldn't pay too much mind to that. Yeah. All right. Just gonna move on. All right. So you also have different types of summation series. So these are just more shortcuts. So any summation that has here, let me pull this up. AK plus B, where A is a constant, where A and B are constants, and K is the summation index, going to be called an arithmetic series. And you can evaluate an arithmetic series to like this formula. So it's going to just be N, where N is the upper bound of the summation, times A of 1, where A is the value of the first index of the summation, plus A to the N, where that's the value of the last index of the summation, all over 2. And then this is what we were talking about earlier. So this is where like a geometric series. So those are going to be the ones where it's like with the exponents. So you could have like you have a constant 4 is r to the n or something, where r is a common ratio and n is the summation index. R would also be a number, but I'm just, for drawing's sake, you could evaluate this to actually, just so that the form makes sense, I'm gonna write this as a. So a is a constant. But yeah, so you could evaluate this to this formula, which I don't think is on the closed form. So I would remember this. So it's, yeah, a of 1, 1 minus r to the n, and then that's over 1 minus r. I think there also is a separate one for exponents. I'd have to check. And then this is for, like, this is the same thing, but this is if the upper bound is infinite. Yeah. I've never seen an infinite upper bound like on the FE, but it was in Guha's notes, so I might as well just might as well just include that in the slides. All right, so to the problems. These are like really just algebra heavy. You just have to like manipulate the summations, but I promise that's not the hardest parts of these. It's gonna be the algebra. But like it's really easy to get partial on algebra, so I wouldn't be too discouraged. So here we have two nested summations. So what you do is, if you've taken like calc, you basically just evaluate the inner one, and then you take those terms and evaluate the outer one with those terms. It's like a double integral for those who know. If you don't, it doesn't really matter. So what you do, so we would just go to our first things first, because this is already in a closed form. So we just go back and we check our formula sheet for what the closed form for this is. It would just be I. So we know it's n times n plus 1 over 2, or whatever the upper bound is for that. So we can just go ahead and plug that in off rip, and our summation becomes what time is it? 4:18. Okay. Our summation becomes n equal 1. And then it's going to be, so we're taking our upper bound. So watch out for this. Don't just like plug in n, plug in your upper bound I here, which is going to be I to the I plus 1 over 2. All right. And then we can see that our like next summation is in terms of I. So yeah, we can do it that way. So first things first you can do now is you can go ahead and pull out the 1/2, because it is a constant, and then you get 1/2 the summation plus 1. And then from here you can split up the summation because you're adding, and I guess you first want to distribute the I, and then so make it easier. 1/2 equal 1, and then you have I squared plus I. And then you can split this up into two separate summations. And half I equal 1 I squared and I. Yeah. Yep. Okay, and then from here we have two more closed forms. So just assume I have the formula sheet in front of me. You'll have it in front of you, and then we can evaluate this to be, so the first closed form, 1/2 times all this. And the first closed form is going to be for I squared is going to be n times n plus 1 2 to the n plus 1 over 6 plus the second closed form, which is going to be the same thing that we had up here, but in terms of n this time. So it's going to be n times n plus 1 over 2. And yeah, all that is divided by 1/2 because we pulled the 1/2 out earlier. And then, yeah, like I said, from here, it's just a lot of algebra to try to evaluate this into its like most simplest terms. So the first thing we do is we can put this in terms of like, so since this has a denominator of 6, we can put this in terms of a denominator of 6. And all we have to do for that is just multiply the top by 3 and the bottom by 3, and this becomes actually I'm gonna check. Do we have any questions on like the closed forms in the can we do an index shift problem? Yeah, we don't have time. But yeah, I wish we could, but we're gonna run out of time. So yeah. But yeah, so you can turn this into 3 over 6. And then from here you can pull out the 6 and then just have 1 over 12 be equal to n to the n plus 1 times 2 to the n plus 1 plus 3 to the n plus 1. Yeah. Okay. And then from here, we can like start pulling out common values again. So we notice that both of these are being multiplied by an n times n plus 1. So like right here, right here, we can pull these out of the equation and bring them to the top of our fraction here. We have n times n plus 1 over 12 times, we pulled out both of the n times n plus 1. We just have, we just have 2n plus 1 plus 3, which is just equal to, here, I don't even need to rewrite that. That's just equal to 2 to the n plus 1 plus 4. All right, this is just equal to 2 to the n plus 4 because 3 plus 1 is 4. And then from here, we can, oh yeah, we can pull out. So this is n times plus 1 over 12. And then these are both multiplied by 2. So we can pull out a 2 and have this be n plus 2. And then we know that this 2 is going to cancel out with this 12 and and that's going to turn into a 6 in the bottom. And then we can move the rest of this to the denominator. And that's going to evaluate out to n times n plus 1 times n plus 2 over 6. It's a crazy plus sign. All right. Any questions on that? Nah. All right. All right. Next summation problem it is then. There's one more. All right. Yeah, this one is a little bit harder because you got to solve for A and B. But like I said, it's really just more algebra because like this is already in like closed form. So does anyone notice anything about like this in specific? Like any shortcuts that we went over? Yeah, they can be split. which I'm definitely I'm gonna do it that way. But another way would be, because this is AK plus B, where K is the index. You could do the arithmetic summation formula if you know it, but I'm not gonna do it that way. I'm gonna just split it up. But yeah. So yeah, you split this up into two separate summations. And it's gonna be like to the n, k is equal to 1, k plus another summation of 2 to the n, 1, b. And then yeah, these are both already in closed form. For this, you just pull out the a. For this, you just pull out the b, and then you bring down the 2 to the n. And then for this, you just evaluate the k's closed form. So this would come out to whatever it is. It's like n times n over 1. So it would just be 2 to the n times 2 to the n plus 1 over 2 times a. And then this would be plus b times 2 to the n. And we're going to set this all equal to 7n squared plus 3 to the n, because we're trying to solve for a to the b. So it's just going to end up being a not system of equations, but yeah, just algebra to try and find out a and b. So from here, yeah, it's just, like I said, more algebra. We know that the 2 cancels out with one sec. Yeah, we know the 2 cancels out with the n. So this turns into a times n, 2 to the n plus 1 plus b times 2n. I'm gonna leave this off for now, but just assume that it's there for space purposes. Actually, like a lot of space on the left. I'm just moving to the left, but sorry, 3 to the n. And then from here, we can start distributing the a, and when we do that, we get 2 to the a that we distribute to the a to the n and to the 2 to the a n squared and the plus a. So we have 2 to the a n squared, or we're distributing the a times n, my bad. Yeah, so that's going to equate out to 2 to the a n squared, because this is all one thing. Yeah, and this distributes here and here. And that comes out to 2 to the a n squared plus 2 to the a n plus plus b times 2n, or 2bn.
I think it's just a to the n, not 2a to the n. If I'm not
Wait,
mistaken.
where?
Your second term on the bottom equation, 2a to the n squared plus an. I don't think it's 2an.
No, because we have the Are you right? Yeah, you're right. Yeah, good catch.
Yep.
So to the n. Yeah, because it's just to the 1. Yeah, I can't read. And then yeah, from there equal to 7 squared plus 3 to the n. Holy, as I've never written on an Apple Pencil before, just cut me some slack. And then from here, what you're gonna do is so we can split this. It's really clever here. You can actually pull out the a, and then you have it like split into specific coefficients. So not pull out the a, but you'll see what I mean. So it's like you have 2an squared, right? And then you pull out the n of these two, and that is plus. They both are like multiplied by n. So then you have 2b plus a times n. So you have this times a coefficient of n squared, and you have this times a coefficient of n, equal to 7n squared plus 3n. And then now to evaluate this, you just set them equal to their matching coefficients. So the 2a n squared is going to be equal to the 7n squared. So it's just 2a is equal to 7. And the 2b plus a is going to be equal to the matching coefficient of 3n. So you have 2b plus a is equal to 3. And then you just solve for a, which is a is equal to 7 over 2. And then you plug that in for 2b plus 7 over 2. And that's equal to 3. And then you solve this, and like it's just more algebra, but I can do it in my head. Clearly, it just evaluates out to b is equal to -1 over 4. And then these would be both of your answers. Yeah. So any questions on that? Like, especially if you need to take, yeah, yeah, especially if you need to like clarify on like what my handwriting says, because this is bad. I'm not gonna lie. Just gonna see if there's any questions. Yeah, so this is from spring 2022. It's question 3 on like section C.
Yeah, we got a question from Viggy. How do we get b to the 2n for the second summation? Do you want to go over that, or you want me to take
For
it?
this summation, b to the 2n? Right,
Yeah.
yeah, okay. So for this one, this is, we move the b to the side of the summation. So our summation was, I believe, 2 to the n, with k is equal to 1, and then it's just b inside it, right? So what we did was, since b is a constant, I don't even know if it was k is equal to 1, but it doesn't matter. Since b was a constant, we moved the b to the outside. This is a 6. We moved the b to the outside of the summation, and we had the 1 on the inside. And then from here, this is just a closed form. It's this specific closed form where you just have the constant, right? And then so for that, we just move down the upper bound, and then this evaluates to b times 2 to the n. Does that make sense? All right. Yeah. Okay. Any other questions? Okay. Index shift. So basically, for an index shift, a like way you would know that you would want to use an index shift would be like, let's say you have a like summation, right? And your summation starts at, okay. Your summation starts at like index is equal to 2, and then you have n up here. So, and it's f of n. So you want to evaluate like the closed form of summation, but you can't because your index is 2. So what you would do here is you would just subtract 1 from the bottom bound, subtract 1 from the top bound, and then add 1 into your summation. And then you would be able to get to I is equal to 1, summation of n minus 1 times f of n plus 1. It will be on the outside of the parentheses, but that's basically like when you would use an index shift, and then you would go from there. What if the bottom is like I equals 2 plus 1? So the bottom is I equals 3, 2n. If your bottom bound, okay, so then you would subtract 2n from the bottom bound, and you would subtract 2n from the top bound. So like, okay, yeah, gotcha. All right, I'm gonna go ahead and pass it over to Dylan because I want to leave him some time to explain the most requested topic, which would be recurrence relations. But yeah, if he finishes, we can go over any other questions. All right. Yo, Dylan, you there?
Yeah, I was just swapping over to my headphones because I had the Zoom on speaker, and if I unmuted, it would have been like an infinite feedback loop, and it would have been terrible, and y'all would have flamed.
Oh yeah, I got you.
I just had to move over real quick. I think I am host, so I can, do my thing. Let me get everything up. Let me get everything ready. I didn't realize that was your last section. I don't know why. I'm just pulling everything up. Oh man, how y'all feeling about recurrence? I bet y'all feeling great. And I do know Adam, bro. Adam's my goat. Okay, I do know Lil Bro, but it's fine. Let me the slides up. Sorry for stalling y'all. Okay. So recurrence. I think if I share my screen now, y'all can go ahead and see. Okay, y'all see. All right, cool. Am I right to say that this topic is like one of the most anticipated topics for this workshop? I see so many people asking about it. I hope I do well. Hope I live up to expectations, but yeah, we're just gonna jump straight into it. I will preface by saying that some of these recurrence problems are actually just crazy. But I am going to do my ultimate best to make sure that everyone can understand this. So the first thing that I always like to do when I start teaching a topic is just kind of go over it conceptually, like why do we actually need this? I did the same thing with like linked lists and all those other things. But basically, why are we even bothering with recurrence relations? Well, they're our way to determine runtime for recursive functions. As we saw when we were looking at code, we could look at a bound on the top, we could look at a while loop, right? We could look at a for loop, we could check all these bounds, but in recursive code, it's not that easy sometimes, right? Sometimes there's a lot of different complex stuff going on, a lot of different operations that we have to consider. And so recurrence relations are basically the way that we come to runtime for recursive relations. Yeah, it's crazy. I know. But yeah, it's the same as a recursive function in the same way that we have our base case and we have our recursive step. In the case of this little formula here to the right, this absolutely despicable evil formula to the right, our base case occurs at 1 and it returns 1. You can almost think of it as like a recursive function. And then our recursive step is calling itself with n minus 1 being multiplied by n plus 1, right? So I've kind of narrowed it down to like, I'd like to say 3.5 steps, but like 3 steps ultimately to try and solve a recurrence relations. So also wait, when I go through them, I don't know if y'all can see, but the one that we're on is bolded. I don't know, like it's kind of hard to see, but it's fine. Yeah. So step 1, you're gonna want to perform a minimum of 3 iterations. Some problems give you partial for 2, others give you partial for 3. So why not go ahead and just perform 3 iterations? And just doing those 3 iterations is legit half the credit in most cases. So just if you have to, just run out some iterations and then leave it as is. But essentially what an iteration is we continue to plug it into itself, right? So the best way that I could explain that, right, is as you see here, we have this equation. This is the very, very first equation, right? We're saying that t of n equals 2 of t to the n over 2 plus 1, right? So then we go, okay, well, what is t n over 2? What is this part right here? Oh, that's a little close. I can't even undo. That's kind of scary, y'all. Anyways, here, there's a t in here. There's a t in here. Okay, cool. So what is t of n over 2? Well, luckily, we have a formula to solve for that. T of n over 2 is equal to t, this equation right here, right? Because technically, if we plug in n over 2, that's really n over 2 over 2, which is n over 4 plus 1. But that is not all we have to do for an iteration. What we have to do is we have to go back in here and plug it in, right? So basically, we know that this is t of n over 2. So we plug that in for t of n over 2. Notice right here, again, t of n over 2. We plug this in to the equation to get this, right? Can everyone see that relationship going on here? This right here is t of n over 2. This is also t of n over 2 right here. And then this is t of n over 2. Notice how there's kind of like this relationship going on, right? So we then plug this in and simplify. So as you can see, we distribute the 2 over to the 2t, which now becomes 4t. We distribute the 2 over to the plus 1, which now becomes plus 2. We simplify, and it is plus 3. This is considered one iteration. This is all 4 or 5 of these steps consider an iteration, right? When we have t of n, we plug everything in, simplify all the way back down to t of n again. And this is our first iteration. Technically our second, because this is our like t of 1 almost, right? But you need to do this 3 times, okay? If you want the highest odds of receiving partial. There are some exams where they give you partial only for 2. There are others where they give you 3. So just go 3. It's the safe bet. We want to rack up as much points as we can because it's really easy to mess up along the way here. So yeah, go ahead and do that. Moving on, we have our next iteration, right? So if you look here, it's the same just again. We have this new equation, which we obtain here. We can bring it down. We have t of n equals 4t of n over 4 plus 3. Well, gee, what's n over 4? I'll tell you. We can go ahead and plug in n over 4 again. So remember, n over 4 is really just n over 2 over 2, right? Which is n over 2 over 2 over 2, because the parameter right here, as we can see, t of n equals t of n over 2. So n over 4, we plug it in, the parameter now becomes n over 8. In the same way, if we plugged in n over 8, it becomes n over 16. So you got some questions in chat. Okay, cool. A meow and an n over 8. Crazy. So we have this, right? We have now, once again, solved for t of n over 4. Our next step is to go back here and plug it in. So as we can see here, t of n over 4 equals 2t n over 8 plus 1. We put that in here. We evaluate again, carrying the 4 over, making it an 8t, carrying the 4 over to the 1, making it a 4, adding it together, boom. Here we go. So now what I want to do before we move on is I want us to basically walk through the steps to, I wish I had like an array. Yo, wait. No. That's too drastic. No, can I erase partially? Sorry, y'all. I'm trying to erase to make room. I want us to do another iteration together before we move on. There's a laser pointer? Okay, I am just going to have to erase all of it, okay? So what I want us to do now is I want us to find the next iteration after this. So we have 8t of n over 8 plus 7. Okay, we want to know what t n over 8 is. What is t of n over 8? Well, we have this formula to go ahead and find out. So t of n over 8 equals, someone write in the chat what this equals. I want to see somebody. Okay, I want to get a little test going on, making sure you guys know when to do what when. Anybody? Perfect. We have 2 answers. So we have 2 of t n over 16 plus 1. Okay. Now, what are we to do next? Just conceptually speaking. Plug it in. So we plug it back in here. We are now left with 8. We plug in t n over 8 equal to this because we figured out that that's what it is. So 8 times 2 to the t n over 16 plus 1 plus 7, right? So now we're almost there. We just now need to distribute this 8. So this will end up becoming 16t n over 16 plus 8 plus 7, and this actually equals 15, right? So this is the third iteration that you're going to want to have on your exam, just to make sure you're extra lucky with partials. And I'm pretty sure they were doing that with more recent exams to give students more opportunity to get partial. This should be plus 15. All right, so this is our third iteration. Does everyone understand how we got to that point? Because I'm taking extra care with this. I don't want to move on until we're good. Even though we may run like 15 minutes over time today, but ultimately in the name of recurrence. Okay, cool. Everyone's looking good. So we can move on. So now that we have this, I'm not going to redraw it again, but we have this iteration, right? Once we iterate a few times, we will be able to, is that formula always correct? What formula? Plugging it into itself? Is that what you mean by the formula? Just like plugging it back into itself? No, the top one. This one right here? Yeah, so this is our recursive step. This is always going to be what we plug that thing into. That is just the formula that we have. There is no like way that it becomes incorrect. You have to make sure that you plug it into that formula with the new parameter, right? So essentially what we're saying is, hey, we have 8t n over 8 plus 7. Well, how do we expand this? Well, we know that if we plug in n over 8 equals, so like for example, t of n, well, what if we plug in, let's say we plugged in t of 4, right? That's going to equal 2 of t to the 2 plus 1. Essentially, we're just plugging in a constant. But what if that constant still had n in it, right? So we're just plugging in n over 8 and filling that in wherever n is. So n over 8 over 2, that's going to equal n over 16, which is what we got right here. And yeah, so that is like what we have to do. Why isn't finding t n over 16 the fourth iteration? Yeah. It's because that first one is kind of like, it's not necessarily an iteration. You want to be, honestly, it's just better safe than sorry type of thing. You know what I mean? Because partial, we want to rack up as much partial as we can. Anyways, once we have 3 iterations, and again, I keep saying 3 because partial credit, right? But that is not a 3. That is crazy. I think I know the erase key behind. Let's go. Okay. Once we have 3 iterations, we want to find the iteration, the pattern that we have in terms of an arbitrary value k, where k is the iteration. So, for example, no, you actually are right. This is the first iteration. So sorry. This is the first iteration because this is base case. So this is the first iteration. Keep that in mind. I am so sorry about that. But with that being said, then forget it. It's not a minimum of 3 iterations. It's 4. Just do 4 steps, okay? Or 3 steps so that you can get my maximum partial. Anyways, the reason I say that is because when you express it in terms of k, this is k equals 1, okay? But anyways, we express it in terms of k. K is basically saying, okay, what is it going to look like in terms of k on the 10th iteration? If we solve it in terms of k, we will actually be able to find what it is on the 10th iteration without having to plug it into itself over and over and over and over again. So I'm going to go ahead and draw out the first few terms we had of this, right? So this is technically our first iteration. Sorry for the confusion. Our next iteration was 4t n over 4 plus 3. We had 8t n over 8 plus 7 and 16t n over 16 plus 15, right? So we are basically trying to find an arbitrary value k that can give us this iteration without plugging it into itself over and over and over again, right? So in the case of this problem, you're very clearly able to see it because it's already on the screen, but we can think about it like this. So for example, This is our first iteration, right? Right here. This is our first iteration. 2 to the 1 is simply just 2. T over n, or T of n over 2 to the k. 2 to the 1 is 2. This is correct. Plus 2 to the k minus 1. So 2 to the k is 2 minus 1, 1. Boom. We then move on 4t again. So it equals 2 in this iteration. So 2 to the 2 equals 4. N over 2 to the 2 is n over 4, correct. And then 2 to the k minus 1, that's 4 minus 1, correct. And so as you can see, we have a formula where we can solve the equation for a kth element, right? And that's important because we need this to solve the recurrence relation. So the best way that you can kind of do this is just guess and, or not guess and check, sorry. Come up with a formula, and if you want to check, go to your iterations and see if you can solve it the way we're doing right now. Same thing. Third iteration, 2 to the 3, that's 8, correct. N over 2 to the 3, that's also 8, correct. 2 to the k, which is 2 to the 3, which is 8, minus 1, that is 7, correct. So you can go here, make sure your k is correct before you move on, because if it is not, you will have, you won't get points moving forward because you will end up solving incorrectly, right? So we have now found k for the kth iteration, right? We found a formula to successfully determine that. Why is this important? Well, if we have this expressed in terms of k, the issue with recurrence relations is that every time we plug it into itself, there is always a function of t. Why is that bad? Because we've never gotten to the point where we can have like a closed form where we can figure out what it is. Everything is still calling itself over and over and over and over again until what? Until this base case. That is very important to think about. It will run forever until the base case is reached. So what are we able to do? Well, what if we make this the base case? We know the base case of t of 1. So let's make 2 or n over 2 to the k equal 1. And if we can do that, we can solve for k for some arbitrary value that we'd get with some algebra, right? And then we can plug that in for every instance of k, except for this one, right? Assuming that we set this equal to 1, we can actually replace this whole thing with the base case and make it 1. So you would then result in, let's say this arbitrary value, let's just call this c for now, right? So this would result in 2 to the c times 1 plus 2 to the c minus 1. And then that will be in terms of n, and that will be a closed form relationship. We will not have recurrence happening over and over and over again. And so that is what we need to do. We need to get there. Like, we need to get to that point. And so here's what we do, right? So perform the iterations. We have that, check. Express in terms of k, check. These two are kind of together. I usually, when I explain this to friends, I call this 3.5. But because this is a smaller step per se, but it's still, right, two more steps. So we have now solved for k, right? Plug in a value of k such that n over 2k equals 1. Why do we want it to equal 1? Can someone remind me? Base case. We want to make it so it's the base case so that we are able to plug in a constant so we can stop the recurring over and over again. Keep in mind that it's not always 1. There are problems where base case is t of 0. In that case, you have to set this equal to 0. You have to make sure you pay attention to the parameter of the base case. So we know that n over 2 to the k equals 1. We multiply the 2k over, which gives us 2k equals n. Substituting that, we get this. So 2 to the k equals n, right? This is fine and dandy because the all places we have k, look, k appears here is 2 to the k. K appears, we don't care about this because remember, we're setting this equal to 1. We don't really care about plugging in here because what's going to get plugged in here is t of 1, which is just 1, right? And then the other occurrence of k is 2 to the k. So if we know that 2 to the k equals n, hey, we can go ahead and plug in an n here, go ahead and plug in an n here, and then at this point, all we need to do is simplify. So we have n plus n minus 1, which is basically just n plus n minus 1, which is 2n minus 1. Simple algebra, but that is essentially how you do it. It boils down to 3-ish steps where you want to, hey, give us 3 iterations by plugging it into itself repeatedly. Then you're going to express the iteration in terms of k. Then we solve the internal parameter of t. That parameter, I probably shouldn't have crossed it out. It was this, equal to 1. Once you do that, you are able to replace with whatever you solved with where this can be substituted. Basically, your goal is to get rid of t to the n by solving equal to the base case and replacing it with a constant. But your other goal is to make sure that all occurrences of k are removed. K is our way to get here, but it should not be in the end. Why? Because we're looking for runtime in terms of n. So the biggest tip, I would say, is to make sure, should we only ever do log to, they say a substitution like that is useful. Sometimes they'll tell us a substitution is useful, but there's multiple ways to do math, and so maybe they won't always be the way that you solve it, right? So what I'm going to say here also, technically 2 to the k equals n, right? You could also say that log 2n equals k, right? That is something you are able to do. But keep in mind, log 2, okay, if you have something like here, let me do this. I'll go over this too, because notice how this is a little weird. For me personally, I like always setting k equal to, like, I want k isolated, right? So n over 2k equals 1. This also means that n equals 2k, which also means that log 2 n equals k. Why is that? The best way that I would describe logarithms through words is what exponent of 2 gives us n. And we know from here, it's k. That's the best way I like to explain logarithms. What exponent of the base gives us a? That is what a log is. And so the answer is k in this case, right? So now we can go ahead and plug that in as well. We are left with 2 to the k t n over 2 to the k plus 2 to the k minus 1. Well, here's the thing, right? If you have, let's say, b to the power of log b a, this cancels out. So if you have the base to the power of a log with that base, this cancels. So in this case, we're replacing k because we know k equals log 2 of n. So this is being 2 log 2 of n. Keep in mind, again, this cancels out because of this rule right here. And so this really becomes n. And if we look here, hey, that is the exact same thing. Same thing over here, right? This becomes 1 because it's base case. So we have t of 1. And then again, we have here, we have 2 to the log 2 of n, which is just n minus 1. And this is the exact same thing. So keep in mind that there are always 2 ways to do something. So to answer Daniel's question, that thing that they say log 2n equals to k, we are able to do that. Notice how we arrive to the same conclusion either way. It really just depends on how math savvy you are and how you choose to approach things. But notice how I just solved that in 2 completely different ways. With that being said, unfortunately, it is 5 o'clock. However, I will be going into practice problems. I'll be doing 2 of them. So if you choose to stick around, that's fine. I am able to stay another 30 minutes or so. So if I see the participation count drop, I understand. But if anything, this will be recorded and published for you to watch later in case you have something you need to do right now. Okay. All right, guys. Another thing, I really want to iterate. I really want to iterate this. Y'all need, you really should to, you always should remember to iterate 3 times. Yeah, if you get all 3 of those iterations right, that's typically 6 out of 10 points. Solving for general form is another 2 out of 10 points. So like solving it equal to k, and then actually plugging it in and simplifying it is another 2 points. I'm pretty sure. For most recurrence relations problem, that's how it tends to go. So keep that in mind. That's like crazy. Like that's wild. You might even be able to just solve equal to k. Do this problem. No. Let's see if I have time. Let's see if I have time because I have other problems that I wanted to do, but I might be able to do that one. That one has a terrible average. So we'll see. If I'm feeling kind-hearted, I iterate 3 times. Okay. If I'm feeling nice, I might go over that. I can explain that over disk if you want. Goat. So yeah, let's get into it. Evil recurrence and evil recurrence too. Craziest part is these probably aren't the worst recurrence I've seen. Y'all follow me on LinkedIn. Peep the post. I'm gonna do this one first. FE prep only has 2 problems, and they're like the 2 hardest recurrence problems I've ever seen in my life. So I'm like, okay, let's do something not evil. Also, partition function, kind of crazy. I need to freshen up on that. Also, I don't know why they just didn't say closed form or exact. Like, I don't know, bro. Let me go ahead and get a screenshot here so that I can get on over to the goat, Excalibur. I know, you're right, if we solve the most evil one, but I was thinking about time, and then I realized time is out the window anyways, so I might just end up doing 3 for all of those that want to stay. Just because, I don't know, I'm a kind-hearted man, I guess. So, booyah. Whoa, I drew a rectangle on it. Where to go? All right, cool. So, okay, we have iteration 1, and I'm just putting this down because, you know, it's best for solving for k. When I say iterate 3 times, I guess that technically means go up to the 4th iteration. You just want to do it 3 times, okay? Cool. I'm going to keep track of my iterations over here, and while we do all of the fancy algebra, I'm going to do it in this text box, just so it's not like crowding up, just so we're able to keep track of what our iterations actually are and what we're looking at, right? And I know this one's easier. Let's warm up to it, all right, guys? Let's take it slow. Wait, is this the one I just did? Wait, brother, did I? No way. Y'all, it's the same one. It's the same one. Wait, guys. Okay. My bad, guys. I will go ahead and skip that one because it's the same exact one. I was like, damn, this looked familiar, bro. Which one is this one? Which one's the other one? The May 22 is May 22. All right. So let's get tragic with May 22. What is this? Huh? Whoa. I gotta look over that. Anyways, not this one. Okay, they finally said it exact for the runtime. Now we can go ahead and do this one. Ba-bam. Okay, cool, awesome. So this one's a little interesting because we have this little term going on over here. Again, I'm gonna go over here and kind of take track on 2 sides. It's kind of how Ahmed taught us to do it. But yeah. Okay, so we have our iterations. Again, our first iteration is going to be 4t of n minus 1 plus 2 to the n, right? Exponents are a bit wonky on this. There's nothing I can do about it. They added AI to Excalibur. Okay. You know, they tried adding AI to Dropbox. Some people are just, I don't know, they're kind of crazy. So let's go ahead and do our first iteration, right? So again, we have 4t of n minus 1 plus 2 to the n. Well, what is t of n minus 1? Well, I can tell you. It is actually, so t of n minus 1 equals 4t n minus 1, which really is just minus 2. At least I hope that's something we recognize. And then this is t, or 2 to the what? What is this going to be? 2 to the n minus 1. Nice. Good catch. So whenever there's an n term inside of here, like outside of t, things can get a little weird. So you need to make sure that you pay attention to that, right? So we have to the n minus 1. And then we can plug this entire thing in. Remember, the entire thing back into here. So we now have 4 times 4t n minus 2 plus 2 to the n minus 1 plus 2 to the n. Right? Does that look good? Everyone understand how I got to here? So we now can continue to move forward, right? So we're going to distribute the 4. We now have 16t to the n minus 2 plus 8 to the n minus 1. However, there is some properties here that we can kind of go over that will make this a bit interesting. And yeah, I do say interesting a lot. So for this particular problem, there's a few things that I'd want to point out as a little point to look into. When it comes to exponents, you really need to understand the exponential rules. So a to the 7 times a to the 5, what is this going to equal in terms of a? A to the 12. Exactly. And so for certain problems with this whole recurrence thing, you know, everyone's talking about, we do need to know some of the exponential rules for either shifting, which I'm going to do in another problem, or, you know, this. So if we're thinking about it this way, we're multiplying 2 to the n minus 1 by 4. Now, we know that 4 is really just 2 to the 2, correct? So what this is really going to equal is it's going to equal 2 to the power of n minus 1 plus 2. And what does that equal? Well, that's just n plus 1. So with that being said, I'm going to put that in as 2 to the n plus 1 plus 2 to the n. Does everyone follow how I got that? Making sure everything is good, because that was a little bit of a tricky thing, but that is how we're going to find the pattern in terms of K. That's how we're going to simplify it, and that's how we're going to have to do. Yes, and I hate it. Okay, well, one of the FE prep problems actually makes us do that as well, where we're I'll do that problem after this one, since I was like, okay, I'm going to do 3 problems, but that last problem was a plant, so that was there to make me mess up in front of y'all. The haters are after me, but we'll go on into the other one. Okay, go over that again. Okay, so one more time and then I'll move on. But there is a rule among exponents where if you have an exponent, so notice how a is the base for these two exponents, a to the 7 and a to the 5, right? That is an important thing to notice. They have the same base, okay? Multiplying them together is a to the 12. Why is it a to the 12? Because if you multiply this together, it adds their exponents, all right? So what we're doing here, we come over here, is we are distributing this 4. That is a big pen. We're multiplying 4 and we're distributing. So 4 goes to here, which gives us this, right? That makes sense. But then we're going to multiply 4 times 2 to the n minus 1. Instead of making this 8 to the n minus 1, we instead are going to turn 4. So we have 2 to the n minus 1. We instead are going to turn 4 into 2 to the 2 so that they can have the same base. And remember, again, because of this rule, when you multiply two things with the same base, you add their exponents together. This actually just equals 2 to the n minus 1 plus 2, which is really just equal to 2 to the n plus 1. Does that make sense? And the reason that we're doing that is because we can have everything in terms of 2 so that we're able to see the pattern easier, because it's going to be difficult to see the pattern if the bases change on us every single time we do a problem. Okay? So we have this. Now, this is an iteration. This is one of our iterations. We have ran all the way through it, right? We're good. We have come to the next term. Now we're on n minus 2 instead of n minus 1, right? So let's come over here. This is our second iteration. All right. Is everyone good on how we got that? This is now our second iteration, and we can already start to see a bit of a pattern here. Now, could we just jump and solve for k? I think we should iterate 3 times. I don't know about you guys, but I think we should iterate 3 times. So I'm going to iterate 3 times. On to our next iteration. We now have this exact thing right here. I'm going to go ahead and delete everything up until this point. Is there anyone in objection to that? Just kind of like clearing the whiteboard. If you need to go over this again, the Zoom meeting is there. If I have 3 people object to me wiping the board, then you're in objection. Okay, Adam's in objection. Adam's in objection. Anyone else? Are we going to let Adam go alone? He lied. He's afraid to be the only one. Period. Okay, I'm taking that as everyone's fine. Scrapping the algebra board. We're coming back to square one. Why does it keep copying and pasting? Okay, so we have this. Okay, now moving forward. Again, we have t of n minus 2. Well, what is t of n minus 2? Well, I'll tell you. Our base equation that we're given is this. Ooh. Wish I could see better. I wish I had a pen. Like my life as a little FE tutor would be so much better if I had a pen. So this is O of n, or t of n. My bad. T of n. So we want t of n minus 2. Well, what is that? That is 4t n minus 2 minus 1. Because again, we're plugging in n minus 2 for n, which is being subtracted by 1, which is now giving us this. We all know, hopefully, in our heart of hearts, that is n minus 3. Then, again, we have this. So we're plugging in n minus 3. So this is plus 2 to the n minus 3. Does everyone understand where I got that from? I sure hope so. Moving on. Cool. Great. So this is what this is what t of n minus 2 equals. I should also write that. Sorry, guys. But this is what t of n minus 2 equals. So now we have this to go ahead and plug in for this. So that is what we are going to do. Moving this down, we now have 16 times this whole equation right here that I'm highlighting, which is going to be 4t n, 4t n minus 3 plus 2 to the n minus 3. And I actually should be wrapping these in parentheses just because that's the way exponents work. And it's definitely easier to see in that case. So I'm going to leave it like this for now, okay? And then we have plus 2 to the n plus 1 plus 2 to the n. Where did I get that from? Right here. Again, we're plugging this into here. So we keep all of these terms that come along with it, right? Making sure my parentheses are closed, everything's good. Boom. So now what are we going to do? Again, we have to simplify. So carrying the 16 over, we're multiplying like this, right? We're multiplying 16 to this, and we're multiplying 16 to this. I really wish they made smaller pen strokes. Like I'm on the smallest one. But we have that, okay? So let's go ahead and do that. 16 times 4 is 64. So we have 64t n minus 3 plus, and again, what could we represent 16 as to make this better? 2 to the 4. Exactly. 16 is 2 to the 4. So we're going to have 2 to the 4 times 2 to the n minus 3, which is n minus 3 plus 4, which is just n plus 1. No, I'm doing something wrong. Sorry. This is going to be... I'm doing something wrong. Yeah, it should be n minus 2. So sorry, guys. It should be n minus 2 because that is what we're plugging in. Apologies. Yeah. This should be there. There you go. So sorry about that. Made a catch. So I plugged in n minus 2. So really this exponent should have been n minus 2 because it's the argument that's coming in here. And then this is carried down, right? So it's 2 to the n minus 2 times 2 to the 4, which is n minus 2 plus 4, which is just to the n plus 2. Okay? Plus 2 to the n plus 1 plus 2 to the n. Okay. That is our official third iteration. Now we have to do one more. Crazy thing is, we can see the pattern by now. So actually, we'll just say, hey, the next iteration is, what's 64 times 4, guys? I'm cooked. That's 256. 256 t minus 4 plus 2 to the n plus 3 plus 2 to the n plus 2 plus 2 to the n plus 1, n plus 1 plus 2 to the n. Ta-da! Congratulations. So this is now our iterations. We have all of our points. Big and awesome. We got our points over here. We officially have like a 60% on this problem. I'm good to quit now that we got that. Y'all fine with that? Anyways, let's go ahead and try to find our relationship here in terms of K. So this one is a little bit tricky simply because there's a little bit of shifting going on here. Also, shut up, bro. Shh. N minus 4, N minus 4. No. Right? So first things first, very clearly, our K term, so we can actually just write it like this, is going to be 4 to the K right off the bat. We know that. That's a clear relationship we have here. Also, this should have a T here. My fault. Oh, it's too big. Wait, no. Ooh, there you go. 4 to the K, T, N minus K. Remember, this is the first term. So N minus K, N minus K, N minus K, right? And then we have a little summation going on here. You have all of these adding up together. But keep in mind that in the first term, we have N plus 0. In the second term, we go up to N plus 1. In the third, N plus 2. In the fourth, N plus 3. So we notice how there is a bit of a difference going on here, a little bit of a shift happening with the way our summation is. So what we're doing is we're adding it. It's basically the sum. I don't even know how I'm going to write this. Uh-oh, guys. Sum. It's going to be sum of I equal to 0 because we're starting at 0, right? Like, this is basically n plus 0, okay? So we're starting at 0, and we're going up to n minus 1, because let's say on our 10th term, we're going to have 2 to the n plus 9. So we're going up to 1 before that term that we're going to. In the sense of the fourth iteration, we're adding up to this, right? Does everyone see how we had that? How we made these bounds? We then have 2. That is a big 2. 2 to the n plus I. Right? Because again, on 3, we have 2 to up to 2 plus I. The first iteration, this will be 0. Second iteration, this will be 1. Third iteration, this will be 2. This will be 3. That is the value of I because we're starting at 0. So on 3, we have 2 to the power of n plus I, which in this case is 2. So it's this. Does everyone see how we got this summation? Is everyone able to understand where we got those bounds from intuitively and why we have this as our actual like summation operand? I don't know, bro. This ain't infix postfix, but you kind of get what I mean, hopefully. Why k minus 1 again? Where are we looking at k minus 1? Never mind. Why not n plus I minus 1? When we do that, that's only when we're index shifting, right? The thing with index shifting is, could you have taken 2n out of the summation and had the bound? Yeah. I'm getting there. So I'm gonna do that in just a sec. That's part of the thing, but like I want to intuitively show what the sum is first before I move on. That's gonna be the next step eventually, right? So here's the thing: we know that we do that the n plus 1 or the n plus I minus 1 or whatever when we're shifting, right? We're not doing any shift here. We're like actually just writing this into a summation. That would be, let's say, for example, we wanted to, I don't know, make this 1. We would add 1 to the bottom, add 1 to the top, and add 1 in here. And would be n from I to the 1 to 2n plus I plus 1. Where that type of behavior that you see is, and again, the upper bounds is, so for example, for the fourth iteration, we're going up to our I term is right here. We're going up to 3. So if in the case of 4 is n, our highest exponent that we're going to is up to 3. So it's n minus 1. We're always ending 1 before the nth term. Where is n coming from? That's which term here we're on. So this is n equals 1, n equals 2, n equals 3, and so on. And it, like I said, we stop 1 before. We stop adding the summation at 3 when we have 4. We stop adding at 2 when we have 3. Yeah, so that is where we got that from. Just intuitively speaking, that is kind of where that's coming from. So now that we have this little formula right here, before we do any fancy schmancy stuff, we want to solve for the base case. So we have expressed in terms of k, right? T of n minus k. What do we want to set n minus k equal to? Zero. So to correct the 1, JK, you need to pay attention to what the parameter of the base case should be, right? We want it to match this so we can get our base case. So it equals 0. What does k equal? K equals n, because we add k to this side, and then we have k equals n. So now, n equals k equals n, same thing, right? Doesn't matter. We can now come back here. So we can replace this. Let me see, make sure everything looks good. We can replace this with our base case. Oh, I have to like go down here. So 4 to the k times t of 0. Keep in mind that t of 0 is equals 1. So this will actually just be 4 to the k, because anything times 1 is itself, plus this gnarly summation that I'm going to try to copy. Yeah. Yeah. I'm going to move this down here. I'm going to like put a little extra space in here, right? Y'all get the gist, okay? Now, here's the thing that I want to mention with this problem, okay? In this case, n is in fact a constant, right? The only thing that we cannot move out of this equation is the I, because the I is what's changing. The I is what's the parameter. N will be the same in every iteration of this. Again, 2 to the n plus 2, n plus 1, n. All of these are n's, and they're dependent on input, so it's a constant, right? So what this actually is, remember our handy-dandy rule of a to the 5 times a to the 7 equals a to the 12. Well, if we do a little bit of reverse engineering, this is actually just 2 to the n times 2 to the I. Is everyone in agreement on that? We can see this because it's n plus I, and again, the exponents are added when they are multiplied by each other. So do you see how this equals that, right? Everyone can see how these two are being multiplied by each other to get this? Yes. And so since this is a constant, we are able to move it outside. So we are able to get, for our kth iteration, 4 to the power of k plus 2 to the n, and then our crazy sum. I'm just going to say sum I equals 0 to n minus 1 of 2 to the I. Okay, sorry that is a little funky, but we'll simplify in a sec if everyone's okay with that type of syntax that I've got going on here, right? This is now what we have. Do we know a rule that can help us solve this? Sorry, that should be I. Apologies. Do we know a rule for this? Which rule is it? Can anyone tell me what the name of the rule is and what the actual formula is? Let's see. Use the geometric sum formula. Awesome. There is something that we can do as well before we get started. Hold on, I'm just looking through my notes on this problem. There's, you know what, we can keep going with this. Yeah. So also, we're plugging in n. This actually should be 4 to the n, mind you, because k equals n. We want to get rid of all of our k terms. Okay. So it is going to end up being. This is going to evaluate out to. Oops. 4 to the n. I added an L in here, which is probably what I'm about to take. 2 to the n times, and for the sum, I believe what was put in chat was correct. Oh, that was removed. Let me pull up the geometric sum one more time. I think there is an issue with the current bounds of this sum in order to do the geometric series. Yeah, I do believe it is wrong. The reason is here. Let's pull up geometric series, geometry dash, guys. I want to play geometry dash. So we go from I equals 1 up to n. And we're at I equals 0 up to n minus 1. We fire in the hole. We've hit a little bit of a crossroad here. So let me go ahead and look back to see something here. Yeah, I'm a bit stumped now. Yeah, okay, I see the index shifting formula. So the issue is it's going, yeah. So if it's from I equals 0, notice how none of these fit that formula. So we are going to have to do some fancy shifting stuff going on here, right? Because we have I equals 0 up to n minus 1, which isn't a fit for the geometric formula. And then the other one is from 0 up to n. So we have a bit of a problem there. So what I think the solution is we have to do some fancy trickery going on with dividing things out here. Does anyone have any ideas? You can do a +1 on the summation and a -1 in I. No, I cannot do the second formula because we're going up to. Oh, wait, you're totally right. If we substitute n for yeah. Sorry, guys. It's been a long day. So here's what we're saying, right? We're making the assumption, using the second formula, the sum up to n from 0 of x to the I equals x n plus 1 minus 1 over x minus 1. Also, I think that's an I at the top. Yeah. And that is a, hold on, I'm trying to zoom in. That thing's tiny. Yeah, up to x to the, n plus 1. Yeah. Okay. Sorry, guys. But yeah, so we can do this. But since our n is n minus 1, it's just n plus 1 minus 1. So this is actually going to equal 2. I can actually write this out this way. This will be times 2 to the n minus 1. And this whole thing over 1 because it's 2 minus 1, which is basically just this as is, right? So we are left with this as our equation. And so let's go ahead and kind of solve everything out. So what we could do, and again, this is the answer here. This should be in parentheses because we are going to need to distribute. So we're going to distribute the 2 to the n over here. So this is going to be 4 to the n plus 2 to the, what is the exponent going to be? Distributing this to this. It's going to be to the 2n because n plus n. So the power of 2n minus 2 to the n because remember we distribute that over there. we are left with this formula. How are we going to get all of this figured out? I believe there's something we did wrong here. Let me scroll up. Because I ain't gonna lie to y'all, I got the solution up right now. I'm just trying to see where. Wait, why did I get rid of everything? That's crazy. So we have 2 to the n times the solution of this. And then this expands out. The solution expanded. Yeah, no, I ain't gonna lie, y'all. We got 8 points here. I don't know what to tell you. I'm gonna go ahead and pull up the solution. I apologize for the oversight. I did not run this one through. I'll try to explain what they did here, though, because I can kind of cover up that way. So we've gotten, if we do our self-grading, we got 7 points here. We did all the iterations. We actually did one extra. They didn't require the extra one. We officially solved in general form, and we know that K, let's plug in K. So we got all of this, right? We're missing 3 points. So please accept any reasonable final form. There are quite a few that are reasonably simplified. You know, maybe ours was just reasonably simplified, but let's see what they did here. So we basically took this 4 to the n, or 4 to the n t, right? Our formula that we had. This is plugged in for 0. So now this is basically just 1. Now, my question is, why did they turn 4n to 2 to the 2n? So they could factor it. I see. So what they did here, okay, I see what they did. Okay, so basically, notice how these are 2 terms that they're working with. Yeah, they always do some crazy factoring. So if we turn this to 2 to the 2n, we now have this plus this, but notice how they both share a 2 to the n. So what can we do? We drag that outside right here and leave what's in the remaining in here, right? And what this basically is saying is if we undo moving this outside and make this a constant on the inside, this will be, yeah, they basically absorb this into here and then change the bounds. They do that because yeah, I ain't even how to, yeah, definition of sums. Oh yeah, because okay, this would go, yeah, and we move this over and then boom, right? So yeah, that's for sure. Yeah. They now have this as a solution, and then we move on here. The thing that is bothering me is that we have a plus and minus. I actually want to see solution is 1 step off of the final answer. Wait, you can share Excalidraws? That's crazy. Yo, you're goated. That's crazy. That's sick. Yeah, you're right. And then from here, I just want to do something really quickly. So we have, I want to see if technically our solution is the same. So we have 2 to the n. Yeah, I think we're close. We're fine. Is everyone okay to move on to another problem? I'm probably going to do one more before I'm destroyed by this and I have to hit the road early tomorrow. Please. Okay, I'm going to run to the bathroom. Since y'all holding me so late, y'all going to have to be patient. I'm just going to go to the bathroom. 8 points is enough. All right. Oh, good gracious, I'm back. Making friends in the back. I'm by myself. I'm home, y'all. Unless one of y'all is like in my ceiling tiles with your laptop, there's no friends to be made at home right now. Let's go ahead and move on to yeah, more recurrence. Yay. Does anyone have a suggestion? I'm gonna take one more problem. I am not doing another one after this. I'm sorry, we're gonna run a whole hour over time, and I am tired, and I got stuff to work on. So all I'm saying is, if I was getting paid, I'd be putting in overtime for this, but unfortunately, we are not paid at Night Hacks. So, oh, I'm not gonna sneak peek y'all into Bitwise. That would be bad. We gotta leave that as a surprise. I think I just did this problem, May 22. No, I just closed it. Let's see. There was one FE prep question that was particularly bonkers, if I'm not mistaken. Damn, the fact that there's only two is kind of crazy, and they're both like wicked evil. Hold on. Is this the one that I knew how to do? I gotta look at the. All right. You know what, y'all ready for some madness? Y'all ready for some actual madness? Gulp. Okay. Let's go ahead and do this one. What do y'all say about that? Is everyone good? Everyone good with doing this one? Whoa. Okay. All right. Let's buckle up, everybody. Why is it such low quality? When is this from? I'm actually just gonna go pull this up myself. We got all the time in the world at this point. How many of y'all do I still have here? Participants. 26 of y'all. Yeah, I had a feeling. Screen isn't showing? Is that, can anyone else confirm that my screen is not showing? That's on you. Okay. String 2023 section C. Spring 2023 section C. Trying to get a better quality version of what's going on. Just to confirm, my screen is showing, right? I'm not crazy. It shows. Awesome. Fire. Okay. Let's get into it. Iterations. We know that our first iteration is 2t n minus 1 n minus 1 plus n. I'm sorry if I go a little quicker this time. Throw a question. Didn't we do this already? No, we didn't. The biggest difference is this plus n's kind of makes things a little weird. So again, we have the same type of idea. Okay, what is t of n minus 1? Well, fortunately for us, we know. T of n minus 1 equals 2t n minus 1 minus 1, which is minus 2, plus n minus 1. I'm going to wrap this in parentheses just to kind of make it easier to identify that it's the n term. Okay, so we know this. And if we go ahead and expand this and we plug it into this formula up here, we know that, oh, there's hotkeys. Yo, this is fire. Okay, I'm going to become the like top 500 Excalibur. 2 times this equation above us, which is 2t n minus 2 plus n minus 1 plus n. Okay, y'all can kind of see how that works. Everyone's got a good idea of what's going on there, right? And then we're going to go ahead and distribute. So we're going to do 4t n minus, that should be minus 2. So sorry. I think someone caught me. Could we put n minus 1? Yep. So n minus 2. And then plus 2n minus 1 times distributing the 2. That's actually 2n minus 2 plus 2. Why did I have a plus 2 there? What am I talking about? It's plus n. Plus n. Right? So 2n minus 1 plus n. Plug in n minus 2. This would be n. So n minus 1. Yep, everything looks good. Are we good? Right there. Everyone kind of up to that point. Feeling good, feeling good. All right, chill. Let's go ahead and move on because now we know our second iteration is 4t n minus 2 plus 2n minus 2 plus n. But actually, I'm going to just do it like this. It's going to be easier, I think, to identify the pattern eventually, once we get to that point, hopefully sooner rather than later. So again, we're in the same position. Okay, well, what is t of n minus 2? Well, I can go ahead and tell you that is going to equal t, or 2t n minus 2 minus 1, which is n minus 3, plus n minus 2, because that's what we're inputting here. We then want to, again, grab this formula. Is it going to let me stop typing? We're going to grab this formula, plug it into here, right? So with that being said, it is now 4 times 2t n minus 3 plus n minus 2 plus 2 n minus 1 plus n. Another summation. Of course, it's another summation. And the reason they do this is because there's a theorem to solve all non-summation recurrence relation problems called Master's theorem that they got mad at us for using. I'm pretty sure that's why it's like this. So yeah, they basically just don't want us to see us winning. Okay, so what does this come out to? It comes out to 8t of n minus 3 plus 4 times n minus 2 plus 2 of n minus 1 plus n. Okay, great. We now have this. This is our third iteration. Well, this is our second iteration, but it's the third term, right? Because remember, what do we always... What? What? Okay, well, that's going to stay there. Yeah, that's going to stay there. No, you don't want to learn Master's theorem because you're not allowed to use it on the exam anyway, so don't waste your time. Okay. So again, we're going to do one more iteration because we love our partial credit. And we can kind of see the pattern already, assuming the next one's going to be 16t of n minus 4 plus 8 n minus 3 plus 4 n minus 2 plus 2 n minus 1 plus n. All right, so now we want to go ahead and figure out what the pattern is. We've kind of already figured it out, but we need to figure out how to express it in a formula. I'm going to get rid of the algebra board. I'm going to get rid of this. And, whoa, can I? It's like really making me mad. Okay, so does anyone have some ideas about what we could actually use to express the kth term of this? First thing I notice is that the coefficient of t is always going to be 2 to the k, right? So going to be 2 to the k right here. The inside of t is also usually, it's always going to be n minus k, right? Because we see here on the fourth iteration, we have n minus k. Now, the really big iffy one is this. Obviously, we have a summation of some sort, okay? That is something that we are not going to be able to avoid as much as I'd want to. We have a summation. So, yep, thanks for the thanks. The recording will be posted later tonight once it's done indexing. Same thing as yesterday. I'll send it the slides. So yeah, summation from k minus 1, or up to k minus 1, summation k minus 1. Are we saying from 0 to k minus 1? Yeah, of 2I. No. We're close, but not quite there. So let's explain this intuitively again. On the fourth term, we are going to, we're going up to, so this right here, this is 2 to the 3, right? In this case, this is n, this could be, hold on. I'm buffering, guys. It's, okay, so in this case, in this one, we have 2 to the 0 times n minus 0, right? That is a way that we can describe this one. This one, we have 2 to the 1 times n minus 1 plus that last term. So notice how in the case of 2, I is equal to 1. In the case of 1, I is equal to 0. So that is how we are able to know that it goes up to k minus 1 and it starts at 0. And then the relationship is 2 to the I of n minus I. So everyone's good to go ahead and see that type of relationship right there, right? Like we have this down. So we solve n minus k is equal to 0, which means k equals n. T of 0 equals 0. So when we plug this in, this actually just gets deleted because it's 2 to the n. Well, no, for this problem, it's a bit weird, right? So this is actually 2 to the n of 0, right? And then they use this really wonky, intuitive way to solve. This problem is ridiculous because there is no rule to solve this problem. They are just telling us to rationale it out, right? Because essentially what they say in the result here is, since this is 2 to the n of 0 and the first term is 2 to the n minus 1 of 1. This is 2 to the n minus 2 of 2. Well, I'm trying to figure out what they mean by this. Because if we're distributing the 2, it's going to be, honestly, I'm kind of stuck here too, you guys. This problem is actually just baffling. Because what they're saying is that we have this kind of like sequence going on here, and then it's going to be 2 to the n minus 1 of 2, and this one's of 3, and 2 to the n minus 3 of 4. No, it's not. Do you guys want to see the solution to this problem? Because honestly, I'm about to just hit y'all again with the 7-pointer. I really don't know how they did this. As humiliating as it is, sitting up here in front of 19 of y'all and telling y'all I don't know what the hell's going on. Okay, cool. So I don't know how I'd be able to identify itself, like myself, but I can explain it to you guys. Like I have the idea of how it works here. Am I able to like, oh, it's embedded. Wow, PDF viewer. Good job, FE Prep team. Essentially it's talking about this, right? So this T of n, and remember T of 0 equals 0. So this equals T of n to the 0 plus T of n minus 1 times 1, right? And you see how there's this kind of like pattern going on here where it's n of 0, n minus 1 of 1, n minus 2 of 2, n minus 3 of 3, all the way up to n. would technically be n minus n of n, which I think they simplify for. They multiply the equation above by 2 to obtain this, and then take the difference between 2tn and t of n. What are you talking about? I know, Adam. Why are they like this? And this has only been on recent recurrence relations problems. Keep in mind this was a spring exam. Spring exams off the book tend to be a little harder. Oop. Yeah, this is a spring one. The spring ones tend to be a little harder. So, but you see what they sort of did. Like you see what they did, but it's like why did they do it? Like I don't understand how they did this, or how they even thought to find 2t of n minus t of n. Listen, guys, if my first lecture yesterday was good enough to get you all 25 points, we also get all 25 points of binary trees, everything. Boom, you're like, you don't even need the recurrence, right, guys? Like we're just that good on the rets. Like you don't even need this, guys. You just get your 7 points and be like, yay, you know. Oh, that's recorded. I probably shouldn't be saying that. I mean, y'all will pass 100% because I'm that good. Like, y'all got this. We Night Hacks is great. Yeah, I really don't know this problem. I could explain like any recurrence relations problem pre 2021. I don't know why it got all wicked all of a sudden. I think they caught the people using Master's theorem. I genuinely think that's what it was. Night Hacks 12? Dude, we're gonna be like long gone by Night Hacks 12. That's insane. We're not allowed to come back. Okay. That being said, it's like almost 6 p.m., which is like a whole hour after we said we were gonna end, which is kind of crazy. I don't even think Lewin's here anymore. Yeah, that's crazy. I don't even got a co-host here no more. Like we're late. I don't even know where my Discord's at. Like I just tried opening Discord. I don't know which monitor it's on. It's kind of crazy. Yeah. With that being said, are y'all good to conclude with the evil recurrence for today? I know I didn't really perform spectacularly on those last 2 recurrence relations. However, as a group, we did amass to 7 points. So that's not terrible, but you know, it was in fact a lot. We're not cooked because really at the end of the day, even if you just absolutely bomb the recurrence problem, you can still get a 90. If you get 7 points on the recurrence problem, you're fine. Just iterate, do your thing. I know ultimately we want to strive for as high as we can, but there's definitely a way for you to survive there's a way for us to survive without doing the recurrence problem at all. Literally, iterate 3 times. What did I say, y'all? Iterate 3 times. That's all I got to say. So, I'm burnt right now. If it was a different day, I might have actually been able to explain those. But yeah. Unfortunately, also tomorrow, I will not be able to teach anything. I will be driving home during the time of this workshop. So Lewin's going to carry y'all, but I will be listening on my way home and co-hosting behind the wheel, which they tell us not to do. But yeah. So good luck, everyone. We will be back tomorrow around the same time. And I don't think Lewin and Yusuf will be able to have our little extended segment tomorrow. So do try to keep the questions within the time frame of 2 to 5 so we can get everything covered. Tomorrow, if the itinerary serves me right, we'll be going over. Oh, I'm not supposed to open that. We'll be going over like everything else. Yeah, that's about it. We'll be going over Bitwise onwards, I'm pretty sure. I appreciate all of your thanks. Y'all are awesome. This ultimately has been fun, which is crazy. I didn't think it would be. Yeah, a lot of good studying for me too. So I'll see y'all tomorrow. I probably won't be speaking at all tomorrow. But yeah, I'm going to end the recording and end the meeting so everything can start indexing. And I will have that sent out along with the slides for this section by tonight. So yeah, happy studying once again. And I'll go ahead and pause or end the recording. And